Good morning, everyone. Welcome to the second day of this wonderful conversation between His Holiness, the Dalai Lama, and quantum physicists from Taiwan and the United States. We had a spectacular set of talks yesterday. Personally, I enjoyed it very much. I've enjoyed many of the questions that His Holiness asked. And also in the afternoon, we had a very, very vibrant and interesting discussion. So for those of you who have the time and interest, I invite you to come to this afternoon's discussion as well. So let us get started with the second day of talks. And today, the first session, we're going to hear about something called superconductivity. I'm sure most of you have heard of this. And this is one...
Superconductivity.
This is a type of phenomenon that, in my personal view, would be very, very difficult to imagine in a classical world. By classical world, I would mean something without quantum mechanics that most of us are much more familiar with. So without much ado, let's go to the talks. The first speaker we have is Professor Ting-Kuo Lee. He's an academician of Academia Sinica in Taiwan, and he will be giving the first talk. Oops. Okay, let me flip to the right page so I can give the title of the talk. Emergent macroscopic quantum phenomenon of superconductivity. Please, Professor Lee.
Thank you. Your Holiness, everyone, good morning. My name is Ting-Kuo Lee from Academia Sinica, and it is my great honor to be able to share with you some of the most amazing and beautiful phenomena in the quantum world. As Professor Chen has said, this is not your ordinary experience, but yet this is reality, as I will show you. So as
quantum effects.
As a scientist, of course, we have to be based on everything on evidence. So my first part is to show you the evidence for why the phenomena is so special, why it's so interesting. And then, of course, as a physicist, we need to provide some understanding to realize such a state is possible, and you will see why it's so beautiful. And then, of course, we will discuss okay, superconductivity, the name is needs a little bit, the word needs a little bit more explanation. Super is, of course, means great. Conductivity is super. What does that mean? Of course, most of you probably have learned superconductivity for a long time ago, but let me remind you, in case you forgot, that this conductivity actually is a measure of how the material to carry electric current. It is inverse proportional to the resistance. What it means, if the conductivity is high, the resistivity is very low, or the resistance is very low. Now the resistance, as you all probably imagine in your middle school, that one has put in a battery and a wire connected to a metal, and if your battery has potential drop, you see a current passing through. You take the voltage of your battery and divide by your current, you get a resistance. That everybody probably know this. I'm just trying to remind you what this is. So this resistance represents how easy for an electron charge to move through a metal. And it provides heat if you have resistance. Now, this resistance, of course, as some of you may know, that of course varies with temperature. And in the material side, we all know we have an insulator, semiconductor, and metal you heard all the time. Now, what is a semiconductor? In this plot I show you is the vertical axis is resistance, the horizontal axis is temperature. It varies with temperature. So semiconductor is that at a high temperature, it has a higher resistance, but then it goes down as temperature lower, the resistance becomes less and less, which it just means electron can be more easily go through the material. So it's getting easier and easier to go through. But suddenly at a lower temperature, it becomes difficult again, much more difficult. And compare this with the ordinary metal, which continually go down. The resistance keeps on reducing when temperature is lowered. And that's why this is called a semi, as you can see. Only part of it looks like a metal, and the other part is not like a metal. That's called a semiconductor instead of a conductor. Now, I have not shown you an insulator, because the insulator actually has very high resistance all the time. And this behavior of metal, of course, it goes down very quickly, the resistance. So the electron becomes easier to go through the material. The usual wire we use these days are made of copper. Copper at the 20 degrees Celsius, or somewhere around here, at the room temperature. That's the room temperature of today. Here is a little bit less than that. But then you go down, as temperature lowers, keep on going down. It goes down by a factor 20, means divided by 20. So the conductivity increased by a factor 20. As you go to lower temperature, maybe say 3 Kelvin, you get to a better conductor. So you can carry same voltage, you can carry more current. It's easy. It's like your water pipe in your house getting more easy to flow. And at a very low temperature, however, this resistance is not zero, which is small, maybe 20 times smaller than at right now at room temperature, but it's not zero. Okay? And so this is the usual material behavior we're all familiar with, but it's related to resistivity. Now, the superconductivity was discovered in 1911 by an accident, usually in the physics discovery. And what it means by super, actually, it's a little bit tricky. What do you mean by super? Actually, it means resistance is zero. We just call this kind of phenomena superconductivity. Actually, the real meaning, exact meaning, is that the material has zero electric resistance. That's the definition, actually. And this.
So here the electron that is being, electricity that is being charged through this
but
medium.
no resistance.
So it's I mean, conceptually, is it seen more like a kind of a wave going through, or is it conceptually?
Now we'll come to it. It's more complicated than that. And we'll come back to that point. It will come to that. I will try to explain. But this is a gentleman got Nobel Prize in 1913, after 2 years after he has reached, but actually for the prize, not for discovery of superconductivity, because he tried to lower the temperature. Remember, the zero absolute temperature, 0 Kelvin, that's called Kelvin, it's absolute temperature. And it's minus 273 Celsius. right now we are at about 15 degrees Celsius, and then imagine you have to go down
그게 정확히
280 degree
이게
downward.
정로 당시 그게 당시 가상 정로 가면 되고 살로 오케이
His Holiness was wondering whether they have put the AC on.
Oh,
Yeah.
yes. So this, it is surprised that he found that there is this resistance drops to almost zero. It's very
and it resistance zero. That's super
yeah. He was just trying to go down to low temperature, cool, and until he got about 1.8 Kelvin. That's the record at that time, and he got Nobel Prize for that cooling to lower temperature, almost 0 Kelvin, but not yet. And then at the 4.2 Kelvin, they see this resistance of mercury. Mercury is a metal at the usual temperature, and the resistance suddenly dropped by 4 order magnitude, about 0.1 to 10 to the minus 5, and then dropping to 10 to the minus 8 very quickly. But so this is a phenomena he discovered. But he didn't get Nobel Prize for this, okay? But it's a very strange phenomena because the resistance suddenly dropped by 4 order magnitude. Instead of just factor 20, as I show you, copper from room temperature all the way down just dropped by a factor of 20. But here it's a factor of 4, 5, 6. And actually, the question is right away. And the message here is that there's a temperature called a critical transition temperature, T sub C. This means C just means critical. It means that at this temperature, the resistance drops to very, very small value. The question is it really zero? Is zero or it's just small? So this is a big difference. Of course, that has had a huge debate. Many people trying to repeat this kind of work.
So
but of course, now we know,
Totally.
and this is called a superconductor.
Totally. Just for clarity, so it's not a discovery of a new medium. He's just managed to bring the temperature down for the same medium.
Yes. So it's a very, so that discovery, of course, generates many people interested in low temperature physics. So low temperature become very important. So you want to see these kind of phenomena. And this is showing now we have many superconductors. I've just picked a few because this is a function of time. The time is in the horizontal axis, and the critical transition temperature here. When the mercury is about 4.2 Kelvin, started from here, and then you have lead, niobium, and all the way. Until 1970, 80 something, we only get about 23 Kelvin, absolute temperature 23 Kelvin for the highest transition temperature. And then at 1986, these two gentlemen found this new material that gives you about 40 degree Kelvin, 40 Kelvin for superconducting transition. Of course, then there is a sudden jump to a very high temperature. This is our next speaker, Professor Wu and Professor Chu, that made the important discovery of this new material, YBCO, and that jumped by 50 Kelvin. So now it's to 90 Kelvin. It's above the liquid nitrogen temperature. That's nitrogen usually is in gas phase. If you want it to be in liquid phase, you have to go down to 77 Kelvin absolute temperature, very low temperature. But it's not difficult technologically. And so then you have a right now the highest temperature we can find of material is 136 Kelvin. It's about 140 degrees below 0 Celsius. And now, of course, people are still trying to find room temperature. Can we have a superconductor right now at this temperature without cooling? And then we also find some other material. That I won't go into detail.
Resistance menyek the terma chung dangje and then resistant nyong chimbarwa that the kwanda chungwa juba hako wenza tati ni gyulam di saba zeje ni tu kala kanzam juba kabla ya tadung resistant nyunga ne tu e tablam ze yoreslam.
So the question then, if there's no resistance, we just review very quickly. Why do we have resistance? When your electron moving through the material, why do we have resistance? There's several reasons, but simplest reason is that we have the impurity, disorder, defect. No crystal is perfect. There's always some other things that doesn't belong. And so you're causing charge moving, bump into that, go backward, and then cannot go through easily. So you put resistance. That's very easy to understand. The second one is more interesting, is that actually the atom does not sit there. The atoms are always vibrating. That's how we put in sound here. I'm talking, you can hear it, it's a sound wave, the air molecule is vibrating. Same in the material. If you hit on a metal bar, you will hear the vibration sound. That's the sound wave. And that's the atoms are vibrating. And of course, making the electron moving a little bit more difficult. They will bump into the electron, the atoms, and they hit each other, and they cause resistance. And but as temperature goes down, this kind of behavior becomes less and less important, and that's why this metal keep on increase their conductivity. Resistance getting less and less important at a lower temperature because the atoms don't move very much. But unfortunately, atom will always be moving because that's uncertainty principle. Atom cannot be stationary. There's no particle can have absolute stationary unless it has infinite energy. So this is uncertainty principle. Okay, but that's not important.
Electron scattering.
Yes.
Nare,
Yes.
nare.
With impurities.
With the ion motion.
Tiri tanda di lo gyudu kala ya gyulam le kokyen chewa gyumse kanyasa na gyulam ki ta chacha chorwa ko nalo le ya yang ko re ta matumba rimutumba tsetando yoba de ten genjik che te genyiba di gyulam ki chacha de nalo le ya kanda kurang ki chashe ki du yodu kala du di ki tsugu degi yo maris du di ki tsugu me du kala electron na tang yodu kala du di kubi ki to jab che te yin da tal töja di ma nyong tang we na ane 두기 단 자체되게 차시게 두기도 요구 당해도 충충 두고 그래서 이내가 뒤에 싸우라는 요구마다 내가 샤도 말했어. uncertain principle 돈 시험.
Yeah. So even at the zero temperature, this
loss 그런 문제 약속으로.
So but then so what exactly is the nature of an electron that is going through?
Very good question.
Firstly, you should explain what is the electricity.
Yeah.
Whether it is just
Waves.
energy,
Charge.
energy also, you see, I think there must be some particle.
Particles, yeah.
Without particle, electricity's movement, I think difficult to say.
Yes.
Even light, some particles.
Particles,
Yes.
yeah.
But they are also wave. Depends. It's two sides of a coin. Depends on which way you want to look at. Many things are two sides of a coin, right? Depends on which angle you look at. But they have both. Okay? We'll come to that.
The 가사님이 just generator 말해.
Lare, generator of electricity.
어디 그 잠면저 왕게 로 잠면저 요요요 말해.
So, for example, imagine, just take the example of generator,
Yes.
which produces electricity. So does it make sense to say that
dynamo 말해.
dynamo, depending on the type of material used, you
Yes.
will generate different types of electricity, or is it just,
Same.
No, the same electricity, just different current, amount of how much passing through per unit time. This amount of it's same. Same. There's no difference. Okay. All the metal transport.
맞아, lightning 거로. 딜러로.
So, for example, lightning is
Yeah,
an
there's a
electrical
charge.
charge. Yeah.
Yes. But they also have ion charge. Here we only talk about electron moving. Ion is fixed. There's no ion motion. Okay. In the lightning, they also could have ion charging, ion motion. So that's two different.
Chitan-
Ion, of course, can also move, but here in the material, like this material, ion doesn't move.
Yeah.
But all the atoms sitting there, it's the electron that are moving more easily. Of course, unless,
Our physical also, you see, there's some electricity.
yes.
Oh,
Yeah, that's why they can use the EKG to.
Pumping. So the heart
yeah.
pumping is also
Yeah,
there's an
yeah. That's why
electrical
they can
process.
check your heart.
So from where it produced that electricity?
So where is the electricity being produced in a body?
That's beyond me. We'll talk about that later. But yeah, it will produce. Many things moving will produce electricity. We'll come to that. Good question. Okay, so, but of course, electron also have the same charge, so they would have a Coulomb repulsion. Everybody learned in your school that the same charge will repel each other. So they also hinder the motion of electrons. So then when the electron move in this material, there's many things to make it move difficult. And so the first question is, can the resistance be 0, not 10 to the minus 9 ohm? Just because maybe he has a lousy equipment, very rudimentary. He cannot measure very accurately. So he got to this, looks very small number, but small number is different from 0, as you all know. 0 is a magic number. Doesn't come very often, and it needs a special feeling about that. And so this number could be very small, so many people challenge him. One thing we could...
not relevant.
Not relevant, yeah.
아니 그냥 zero 쓰도가.
나래.
zero 써야지 그 zero를 그게 영어로.
나래.
양그 싸니 그 패니시도가.
나래.
그러니까 어떻게
So
zero 그 저치도가.
나래. But
그거는
zero,
zero로.
yeah, zero is very important because on the other end, zero is representation of an absence.
Yes.
But at the same time, although it may do nothing on its own, but when you accumulate them and then combine it with the other numbers, it has a huge function.
Yes. No, what I mean is that in the real world, we use real numbers. Real number, you can have a many decimal. I can have a 0.01. It's not 0. It's still 0.001. Okay? But I could only have a 0.0000. No matter how many digits, it's 0. That's different, very different, okay? Real number is different from discrete number. You talk about discrete numbers, so we'll come to that. That's quantum mechanics, okay? Then we'll come to this. Now, how do we know it's 0 or not? So you can imagine, I show you, you take this material, you put in a battery, you measure the current. Now, if there's no resistance, like what I show here at the bottom, if the resistance equals 0, you have a battery, then you have current. So what can you do? If you take away the battery, once the current begins to flow, you say, let me take away the battery. What happened? In ordinary metal, you can go home, try it. Before your eye can even blink, your current already gone. But here, you take away the battery, the current can go on for years. Years. We're not talking about days. And it has been proved by experiment. Yes, this is a proof by experiment. And the extrapolation, of course, after 2 years, they are so bored to looking at it, they don't want to do this experiment anymore. Yes.
So totally, let me make it, let me understand this. So what you are saying is that in a conventional case, when you take the battery out, electricity goes away.
Yeah.
But here, because of the 0 resistance, so even when you take the battery that is conserved, that is containing the energy taken away, energy is still
the current is still flowing forever. In principle, it's forever. Of course, nothing is forever. So I say essentially forever. It's connected. It's a loop. So they make this material, they just add and start the current and take away the battery, and then the current just go on. It's a loop. Okay. So it would go on. The experiment lasts about 2 years, I think, if I remember correct. And then they just stop it, okay? Because they cannot measure the appreciable difference. So the extrapolation is, it will go on forever.
간다 로드 서베 쉬고데 로 규름들 고연매나 아니 로디 자나 마조 데디 그래서 그 experiment 제제 로니즈 좀 간도 되버스도 그 규마이나 배터리 던샤나 조도로
This, of course, against all the intuition, ordinary experience we have. But here I'm just saying that, so this is experiment evidence. So the superconductivity in practical is zero resistance, not approximately zero, not because he doesn't have a good equipment, instrument to measure it. So it is a quantum effect. And that right away clarify this is not your ordinary classical word. We talk about not a real number continuous, there's a jump. It's zero. We have to be, so then, discrete word, 1, 0, 2, -1, very well defined. But once we come to real number, 0.0001, 0001, okay, there's many decimal. So what exactly zero is a bit tricky. Here it is very clear. There's nothing, no absence of resistance. So this is also has to be a macroscopic, not microscopic, not like hydrogen atom. It's just one very small thing. Here, this is a big material, a loop of superconductor currents going. We can see it's macroscopic. All the electrons, about 10 to the 22 electrons per centimeter cube, are doing this. No bumping into each other, no resistance. Impurity, they cannot see impurity, defects, they just go through.
다 라베 내가 longo도 교배게 퀀텀 개케죠 샤워 그래서 퀀텀 그 남주 샤워 그래서 라베도 투중한도 그 퀀텀 그 남샤 망보지 두든 참여가 마도 샤도 매봐 사베도면 다다는 디 superconductivity 디 간다 수쟁그 so professor so in terms of the size just to help us the non-physicist here.
I will show you the next, the one, the size is centimeter, or even now they have wires even kilometer long. So the size is not an issue.
Sure, okay.
It's just ordinary material we see. You don't have to be nano material, don't have to be micron. So this is showing there's another interesting property of this material. Besides zero resistance, it's called a Meissner effect. It has a very strange property interacting with the magnetic field. So you put a magnet. This one is a magnet. This is a superconductor. This is just some drawing. This is for the anniversary, 100 years anniversary from a magazine. That you see this magnet levitate. There's no touching. So it's against gravity, it moves upward. Once it becomes superconducting, you below temperature, the magnet lifts up. It's called a levitation, magnetic levitation. So that's another strange behavior. Somehow the magnetic response of the material is different from usual metal.
So the medium material, is it a kind of a human construct, some kind of fabrication?
No, just a magnet, ordinary magnet.
No, the conductor.
Oh, the superconductor is one of those high temperature superconductors we just showed. In his lab. We show this very often to our open house. Everybody can come to see levitation, okay?
The Gandhi Tanadi or Chang Kasati. Jacobin the Mama Java Koya Jate or levitation.
Pointers. Pointer today.
You should say that the current is going through the bottom, goes through the superconductor and going down.
No, this is a superconductor. You just cool it. just make it go to lower temperature. This is actually the liquid nitrogen that cool it. And then this magnet, original setting here, and then just, I didn't show the film. Actually, there is a movie, but I mean, because of time. The magnet sitting there, then you cool the temperature down and the magnet will, flow. Yes, that will come down. Yes, I will come down. Yes, I will come down to that. Yes. I will explain that.
Levitation.
Yeah, I'm just describing the phenomena. No theory, no model, nothing, okay? Just what you can observe. Nothing more than that, okay? And then one realized there are two kinds of superconductors. They, under magnetic field, behave very different. Imagine looking at this line. This is temperature. This is field. But look at this line. You go from very high temperature, you come down to here. Suddenly, you're below this critical temperature. You see no resistance in this part. Now you're applying a magnetic field to this material. The interesting thing is the first part you see is that when you apply the magnetic field is being repelled outside the material. See this shape? That's the superconductor, the field banded. That's what observed by this gentleman called Meissner. So this is called the Meissner effect. And this state called Meissner. So when you apply a field, the field being repelled. Then if you apply higher field, you could just go to the normal state. That's called a type 1 superconductor. Or the other kind of superconductor is, even more interesting is you have a mixed state. The field can penetrate, but not randomly. Penetrate in a very special way. And I will come back to that. This also involves another Nobel Prize. Okay, this is another interesting state. But in all these states, resistance is 0. So the state changes. You don't let the magnetic field get into the material. But it's too strong. They cannot hold it off. You can move in, but you move in a very special way. Oh, okay. The chairman is warning me.
because 장로는 집에 있는 거의 대
Levitation,
지선. 대 카블린티. 저도 그래비티스가 가져 그래.
So, you know, you showed
그래비티스
that
텐슈코 차장도 줘야 돼. 근데 얘는 점리 장마다 점리 로마. 차장 토네 그래비티 저와 샤오시.
Given the effect that we are seeing here, where seems to be a function of primarily of a cooling.
Yes,
temperature.
you have to be in that state, lower temperature.
So the question is, Holiness is
otherwise
asking,
you are in the normal
Sure.
state. Nothing.
So the question is, Holiness is asking is that at some point the magnet sort of bounce off
Yes.
and levitate.
Yes.
So which seems to suggest somehow it's kind of bypassing the gravity force.
Yes,
So
because
does-
there's another force
Okay,
to
so
counterbalance
His
the
Holiness'
gravity.
question is this: so if that
Then I will
means
come down to.
gravity is somehow related to the temperature, does that mean in the Earth
No,
some parts are hotter,
no, not
some
that.
parts are cooler? So does that have a different gravitational pull?
Okay, no, not the gravity is not related. It's this material, the property is related to temperature.
Gravity 계속 말했어.
뭐 디면서 하고 그래비티 말봐.
Yeah, but the reason why originally it was holding is because of the gravity, isn't there?
Yes,
Yeah.
but there's no force to push it back. But once you're below this temperature, in the superconducting state, there's a force to push it. I will show you right away. Be patient. Be patient. I will show you right away. Yes, that's what I will show, the next one. Okay? So we will discuss this, why it's come out, okay? We will discuss, you will see. It's a very logic reason, very simple reason one can understand. Of course, you have to buy certain scenario. But the first scenario you have to buy is this three gentlemen propose a theory to describe what happens, why this very strange phenomena occur. Now, their proposal is very interesting. They say that we probably have a pair of electrons. Electron, instead of moving along like usual normal metal, they actually pair together. How do they pair? They actually has a charge, mass, and spin. So the two electrons, the same mass, same charge, but they could have a different spin. One is a spin up, one spin down. And this spin up and spin down form a pair. Okay? And usually this have equal number of upspin and downspin in the metal. And unless you apply magnetic field, then we'll talk why the magnetic field has strange behavior. It's related to this. So now we have, instead of each individual electron, imagine you have many pairs. So if you have 100 electrons here, there are 50 pairs. They form pairs. Okay, this is called a Cooper pair. And that's a general professor's name, Cooper, and he said that we should have a pair to explain this. And then, let me go then quickly, but the electrons all carry the same charge, supposed to repel each other. How can they form a pair? Where is the attraction come from? They should hate each other, but somehow they don't. What happens? And the explanation, this particular paper, very amazing paper that show that if you think about it, we have iron in the material, which is positive charge. Electron is negative charge. So when the ion moves, one electron sees, this ion, good, they are opposite charge. So he comes, and then he vibrates, there's another electron sees positive charge and comes. And it looks like these two electrons love to be near each other. So they become effectively attractive. Okay, even though they were supposed to repel. But if there's another media to provide a glue attraction, then they become possible. So repulsive become, this is, and so that is the schematic show that two balls actually now become a pair. Two electrons, of course. This vibration mode is the sound wave. So that works. Of course, this theory has been checked billions of times, so many predictions. Now, let's imagine how we understand that. This is the important part. Now, how do we understand all these phenomena? Think about a very huge ballroom. You have playing walls. People are dancing. Many, many pairs are dancing in this beautiful ballroom, following the rhythm. And nobody bump into each other. And there are tables, there are columns, but they just go around. And they exchange partner. You remember, you see the movie, old movie, they're dancing very beautifully, exchange partner, moving around. Nobody is sitting there. Everybody is moving, dancing, but nobody bumping into each other. Just imagine this lady is a spin down electron. The gentleman is spin up electron. Think about that, and then now you think, I have a hole, put the 10 to the 22 electrons here. And they are all doing this. What a beautiful thing. You couldn't think of anything much beautiful, amazing than this. And they are all dancing, because they all dancing in the same rhythm, coherence. There's no bumping, no hitting. Even there's a column, like a defect or impurity, there's table, we just dance. And this is the beauty of this state. Electrons somehow or collectively move in a coherent way. Okay, that's a special kind of quantum. They exchange partner, they can even exchange partner. If they don't exchange partner, this is called another kind of quantum state, fluid. It's called Bose-Einstein condensate. Bose is a gentleman from India, great physicist. So this is what you want to imagine. Now you imagine you have this music playing, huge number of pairs are moving, and they don't bump into each other. And they exchange partners, of course, because here you have a face. Imagine the gentleman has a mask. All the gentlemen, same height, same dress. All the lady with the mask, same height, same dress. You cannot tell who is your pair. You change pair, you follow around. And that's exactly what happens in this system.
Coherence for the
macroscopic now
quantum
state.
Yes. Now,
근데 the quantum 내급 저와
네.
다른 드라베 내급이야 샤투그레스 다른 electron 되게 지기질 규입에 소르지 아니 수수수 다체제 그 송대체서 저와 다체 아니 상만 냠루고 또네 냠보 다른 강부터 홀 침부지나리아 단스 야냐 망부지 바제질이야 단스 샤로 탑기요나 아니 지기질
okay,
규입에
that'll
소르지
be fair. Okay. So, anyway, so let me go quickly. Yeah, in a coherent individual model. So you may still have sometimes one person slip and they get a bump, but that's very small. 1 out of 10 to the 20, we don't really care. Now, let me explain the magnetic field. It's very strange behavior, this Meissner effect. But when you apply field to this, what is exactly happened to electron is they have a different number of spins for up spins and down spins. That is the number. Now you imagine in this hallway, there's more gentlemen than ladies. Then what happened? How do you dance? But each one still want to dance with the lady a pair. So there's always some of them left alone. And they don't like it. Superconducting state don't like it, hate this. And when they hate it, what happened? They are smart. They just push the field outside the wall, hallway. So the field is outside, then you have equal number here, then they are all happy. What the Dalai Lama said, be happier. So they want to be happier. So they get very happy to push the field outside. That's Meissner effect. The field, look at the field. The field is pushed outside. Look at the drawing. Now let me just show you. This is what happened. In reality, what happened is when the magnet here, in usual matter, we all know, it produces shielding current. And this shielding current has the right magnitude that pushes the field. So you see the field is bent. The magnetic field line from north to south is bended. And this bending lifts up against gravity. So you have a force, move it upwards. Otherwise, it will not. So this is the current. So it's a shielding current actually occur in this state, and all the field outside, and everybody is happy inside. No problem, okay? So they know how to be happier. But if you apply stronger field, how do they make them happy? They cannot repair. It's too much to repair them. Then what they do? They're even smarter. They say, okay, I cannot repair you. What I do is I confine you. I make all the field occur in a small region, but separate them periodically, like a column. So now I have all these columns essentially made of this magnetic flux line. This is called a fluxor, quantum flux, made it into a periodic array. This is called a vortex lattice. Abrikosov has a name because he got Nobel Prize 2003 for this work. So they are even smarter. Now I cannot all repair you. So you can join us, but you have to be in certain very nice positions. Then we can still be resistance zero. Okay? So now you see they like to be happier. They are smart. But if you go too much field, then you can see all these quantum flux would begin to touch each other. Then there's no way superconducting will become normal. Okay, so one can explain this line. You go up from here, you first repair, then you confine, then you become normal.
Magnetic field ko nalo electron da marabe ne shenda ne zulen ya to ne field ya churta jik ya ne field sa je di ya nyung ju so je di nalo ya ne quantum effect nya ya da ko ti nam ju dam ta to.
So the dancing continues, okay? And then now just two more, like there, okay? Another unforeseen consequence of pairing in this coherent state is the loss of charge identity. What do I mean by that? You remember two electrons supposed to have the same charge according to Coulomb law. they should always repel each other. Now they do not. So it means effectively they don't see each other as same charge. Okay? This is an unforeseen consequence. When they wrote the paper, they didn't realize. Then they realized this is related to Dr. Lee's yesterday's talk. This is so I won't be bothered. But effectively, is the identity of original electron has lost. In our jargon, we say they change to a different quantum state, have different quantum number. But in simple interpretation is the electron don't remember it's an electron anymore. So now comes the discussion question. Superconducting is so essentially I laid the groundwork for this superconductivity. The next two talks probably are all related to superconductivity, so you will learn a lot more. But here I'm just showing you a very simple picture. Just imagine the ballroom dancing, okay? And they all behave coherently. Defense and intuitivity no longer matters. Do we have an analog phenomena in real world? Interaction between electrons play a dominant role in the emergence of new physical property. It's because of interaction. So now interaction is very interesting, very important. So we talk about isolated electron, we understand everything about it. But when we put 10 to the 22 electrons together, completely different. They behave very differently. They forgot what they were.
Interaction.
The Lodun Pazu, the interaction Chidang Tone, and Yanko Kusung Regatone, and Keju Savage Lewis, that the emergent property.
Similar effect in classical.
And then Jingbatan did not deny some Tantan to your best, Shebat to your best. Now, sure, you need to song the day with Dugalian, Ku Titone, and Mixegi, Keju Savanye.
So we were asked to produce some questions on that. But in any case, the picture is very simple. These electrons paired and they move around, dancing around. They no longer remember they are the same electron in the normal state at a high temperature. They are different. They have a different charge. Spin, actually, I didn't talk about, also different. They are entangled, like yesterday. Each pair is exactly the entanglement pair discussed by two Professor Chen yesterday. And so exactly that entanglement pair. Each one is entangled. So actually, each one is entangled with every other one. All the spin up, all the spin down. That's interesting. But anyway, this is a theory, a model that we use to explain millions and millions experimental results related to superconductivity. And it works surprisingly well, works very well. And, but we still keep on finding new interesting phenomena. But because this is not our common reality, but this is real, okay? Because everything I talk about is being proved by experiment and theory, okay? And, but still, the emerging of a new macroscopic phenomena, and in that state, the electron has lost its original identity. Thank you.
Your Holiness, please. Comments and
comments.
당연히 간다 지 샤르조겠다 가서래 담아 가서잖아 시제 남샤 샤윤드 아니 바나 숙시바 데민 두지스 두제드 두마치 니체 두제야 숙시바 데민 두지스 소소소 오면 잡아도가 좋아 저도 진짜 좋아하는 듯이 야 도스면 자 샤스래 나한테 지금 자장 그죠 Semi-pembu,
So one thing that is sort of a major contrast, a point of contrast between the way in which the physicists presenting reality here versus the way in which a classical tradition like the Buddhist philosophy would look at reality is the way the
다 독스냐고도 근데 계지 직배더니 가서 계속서
나래.
계지 직배더니 대선 직세 계지 미징에 대선 직세 다 계지 징에 대선 나라라 아니 시바 직세 뇨 요제지 다 되는 섬에 편부 직세 다야 지금 메다고다 사업도 제다고 시바의 말 코르지당다 가서 우리 한번 다 뭐부지 샤딩을 다고 되면 주시기도
So, for example, like in the classical tradition, like Buddhism, when we, engage in exploration of reality, the approach is to first come up
I
with a
think
big
not
picture.
necessarily Buddhism, ancient Indian tradition.
Indian tradition, yeah. So, for example, yesterday we talked about the conditioned things, which are constantly changing, impermanent things. So you look at the world and say, okay, there are two broadly different types of phenomena. One is things that are subject to change; they are momentary, impermanent. But then there are things which are not that momentary; they are unconditioned. And within the conditioned world, then you have matter, which has some obstructive properties, which has mass, which has extensions, spatial extensions, and so on. Then you also have another fundamental category, which is what in Buddhism or in the classical Indian tradition would refer to as consciousness or the world of mind, which is the primary characteristic is that of subjectivity. It's a subjective experience. Then you also have part of your taxonomy of the world, reality, certain things which are neither mental nor physical. So, for example, like the attributes of impermanence or time or the concept of person. So those are part of your description of reality, but they're not objects in the world, nor are they subjects of experience. So you make a broad category. So then if you look at the quantum description or the physics description, it seems to be really staying at this first category, which is really about the matter.
Space is the particle holistic.
So the one question His Holiness would like to ask you is, yesterday we were talking about space-time symmetry. So in that context, when you use the word space, is it conceived as a kind of a base composed of particle?
That's what depends on what length scale you're talking about. This is important. In physics, we always separate different energy scale, different length. You talk about very small length scale, you talk about very high energy, you talk about, like material here, we talk about the energy scale is small, electron volts below that. So it's a different, we have a different kind of tools and different principle applied because they behave differently. Yeah. This particular idea that we have a macroscopic quantum condensate of all these pairs actually was used in Dr. Lee's discussion yesterday. So it's used in the cosmology, space-time. Okay, this principle. So what we learn is that maybe learning one material, you say, man, so interesting, it's a material. But the fact is, when we learn from one material, what we learn, the knowledge, actually can be applied to many. Actually, this also happens in neutron star. Okay? So this is the kind of idea seems to be very restricted, but actually it has a profound effect because it brings in many new thinking, and that could be applied to different parts of the...
Sure.
If His Holiness has one last short comment we can do, otherwise we need to move on.
Yeah, I think we can move on, yeah.
All right, thank you.
Thank you.
Can you sign it for me?
Which one is this? A universal single.
In single atom.
Better. 'Cause for you, just. Thank you. Maybe that's better for you. Just.
'Which one is this? A universal single.
'Cause for you, just. 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 Our next speaker is Professor Maw-Kuen Wu. He's also an academician of Academia Sinica in Taiwan. And he will be telling us about superconductivity, a novel quantum state.
Your Holiness, Professor Lee, ladies and gentlemen, it's really my great pleasure and honor today to speak to you on a subject that you have just learned from Professor Lee, a lot of detail about the fundamental physics. So what I'm going to do here is that, as you can see from the first chart, I have two nice pictures which show the structure of the material we are working on. So what I'm going to talk about is, well, very briefly, just remind you what superconductivity are. And then yesterday we have a very vibrant discussion. His Holiness also talked about, as a scientist, we should be doing something good for the humanity. We should not do something destructive, right? And so I'm going to just show you a little bit about what superconductor can really do for human society. Okay, so it's an application that has been already going on. And then I talk about some of the recent discovery on superconducting material. But my focus will be the last part, to talk about what this interesting phenomena, but what kind of material, what do we learn now? Of course, it's an open question. We still are not sure what's going on exactly, but there is some hint. Okay, so I'm going to show you what we know today. Let me just remind you quickly the zero resistance, as Professor Lee mentioned, and the so-called milestone effect, which has the perfect diamagnetism, are the two pillars of superconductivity. And that leads to this interesting phenomenon. It's not just levitation. You can suspend it. The magnet here, the picture shown here, this is the magnet. This is the superconductor that cooling below this transition temperature. It's not only just levitate, but it can suspend it down slow. That exactly can be explained by Professor Lee's last paragraph. You have a different field. The field penetrates and forms into the vortex core. And then essentially then you have attraction and repulsion together, so you can show this kind of behavior. So this is a real interesting. So this, I don't know why it didn't go. Oh, sorry. Go back. Okay, so this is the true novel quantum state that can be seen macroscopically. You can sit on the table while it's going. If I have a chance to bring the liquid nitrogen here, then we can show it today. But anyway, so this is a macroscopic phenomenon. Okay. And let's see what it can do to human society. As we mentioned, the zero resistance, so we can make it into wire that can carry current, transmit the power without any energy loss. Okay, so that is already going, and there is the proposal. Well, maybe one day we'll see this kind of supergrid thing using superconductor to connect all the electricity that save a lot of power, especially if we have power from solar, from wind, and we need a better transmission to do that. Okay, and this is our dream. Hopefully, you can see that in the near future. And we can have a high-speed, real high-speed train. And this is the true model in Japan, has been running for several years. It's a 20-kilometer long track. It's a levitation train. And this train can run up to 550 kilometers per hour. That's the test right now. But in principle, if you put in vacuum tube, then you can go up to 1,600 kilometers per hour. Okay, it's energy saving and so on. So that's another dream we hope to come true. And there are many medical applications already going on. And this is the special device called, using this very sensitive superconducting material. There's a phenomenon called quantum interference effect. It's related to the quantum phase idea. And we can use this kind of a superconducting quantum interference picture to make in a device, which has a very sensitive detection to a small signal. Johannes, you are talking about the heart may be beating, you give some electricity. So we are using electrograph, easy to match that. Now we can use this squid because the small signal, you can give you a dipole, a small magnetic signal. So you can use that to detect the heartbeat. And the beauty of that is not only to see you, especially for a pregnant woman, you can see both the infant, the baby, and the mother without intrusion. Okay, so that's the very beautiful application for that. And we can look at that. It's already been going on for years in just the brain science.
투지 사버스 제 단어 superconductive 잘라 배주 제네 단어 투지 규모가 저바 전부터야 망보지 대체도 그래서
Okay.
So basically it just becomes much more sensitive to the
very
smaller
sensitive.
signals. Yeah.
Right. Very small signal can give it out. So like a brain wave, this is the for brain signal, okay, and has been using. And of course, everybody know about this MRI, okay. This is essentially using this superconducting magnet. Professor Lee talked about if you have a current in a loop, and without even charging, it continue flowing, the magnetic field will be in there. So when you cool down and set up, it'll be there for, okay, forever. And we can use that for very important high energy research. The so-called gas particle, the Higgs particle was discovered in this machine, and mainly because they have such a high magnetic field generated, reaches such a high energy. This is a picture that from Academic Seneca that we have collaborated and built a very large array of a telescope. I think Professor Lee really make a major contribution to get the money to do this. Okay, and this is important for understand the universe. And the key component is using superconductor to detect the signal. And we can also use the device to evaluate, like an aircraft. Is there any crack or any material has a failure without any, non-destructive evaluation. So there are many, many applications is going on here. Okay, so I think the superconductor become more and more important because of certainly this potential application for human society. However, there's a question we critically have to ask. Well, as Professor Lee mentioned, you need to cool the material down to a certain temperature in order to see the property and the function. So we need to find a material that whether we can have around room temperature or even higher, so we don't need this complicated system.
Not need to use complex 가수도디.
간다 장무소액.
가.
장무소액.
알레.
단다 구주디 에너지 컨서베이션하고 제도야 되고 규람기 작자디 장무시고 속으로 봐. 근데 소모고 돈에 답시 여러분 스타트 강행들에서.
So we need to, so this is the important part, what we are working on, try to find different kind of new material. And this is the reality, this is interesting phenomenon, but what's the real world we are working on? And Professor Lee mentioned that since the discovery from 1911 up to 1986, over 3/4 century, the increase of the superconducting temperature is very slow. Okay, so but fortunately, two scientists from Switzerland found this particular material. I'll come back to that, okay? And that shows superconducting property, not that high, but it indicates there's a potential that you have something new, different. Because this material, if you look at it, without this barium here, if I don't have the barium add-on, is an insulator. It's a very poor conductor, not conducting at all. Only I replace a little bit of lanthanum by the barium atom, it suddenly become metallic and then eventually superconductor. Okay, so we have a new paradigm to look at. And very luckily, I was in the US at that time in Alabama, and my student and I in the lab. Well, in '87, I find out another set of a material, which is shown here with this structure. And the interesting is this material has 3 times higher transition temperature. Okay, okay, and then later on, okay, this is the search now going almost 30 years. We're still looking for this room temperature. We call this the holy grail of our superconductivity. Now, then we have, as a scientist, then we have to understand why this material compare with the previous one, this left side here, and the right-hand side here. Why the transition temperature can have a 3 times difference? If you look at the basic units, it's the same. Here you have a copper oxygen as a plant. And with this is oxide, oxygen. And with some lanthanum, well, this is kind of cubic, distorted. But in this, if you look at, on one simple way to look at it, it looks like that I'm cutting this A-phase system, octahedron, right? And then cut into half. Now I have a 2 pyramid. And somehow in between, let's insert another element. But in the meantime, in this part, I take some oxygen out. And I have a 2-dimensional become just 1-dimensional Chen from the structure point of view. Then the superconducting property is different. However, of course, we know the superconducting all still coming from this region, this plant here. Okay, here I want to remind you here, in this system is the barium replace a little bit of the lanthanum atom. Okay, original is the 2 lanthanum, 1 copper, 4 oxygen, form into 1 unit. And when I replace a little barium, then it becomes metal and superconducting. And in this part is 1 yttrium, 2 barium, 3 copper, with 7 minus X. And this X is important. If I have a 0.5, like a 6.5 oxygen, this material is an insulator. It's not not conducting at all.
그것은 거래. 스페이스 그룹 스타디.
작절이야 넘베잡지. 다다 superconducting 용해리야. 그래서 고게 맞게 개치쇼인 봐. 다 고게 맞게 탑셰리야. 아니 제 넘베잡.
Okay, so the material really rich, really beautiful. So I start making slightly the chemical change. Here I change into the barium, and here I add a little bit more oxygen. And that's gold. So the material base for all this copper oxide material to become superconducting is to introduce electric carrier. Yeah, to introduce electrical carrier to the original insulating material by changing chemical stoichiometry, either by substituting element in with this so-called 2-1-4 system, or changing oxygen concentration in 1-2-3. But a theorist like Professor Lee, then he would say, yeah, this is your material world. But as a physicist, what is this? That's what his picture will tell you. He said, in this original insulating material, okay, as I mentioned, there's a copper oxygen plant, copper oxygen form. And every copper has 1 electron, you know, because the D electron, and you count it, it has 1 extra electron. And every electron has a spin. So it occupies one side. And because you have an electron-electron Coulomb interaction, and this electron here, if I want to bring another electron in, it costs a lot of energy. You know, it's like your hand is sitting here, we squeeze in too much energy, right? So this seat can handle one person. So I cannot move.
거기서 지리야. 참가자면은
So in this case,
도토자 들어와서 그럼.
yeah, in this case, I have to quietly sitting here. I cannot move. All the electrons have to be sitting here, cannot move. So there is no conducting. Electron cannot move around. You cannot carry.
톡제가 속 토닉 속 시다.
Yeah, yeah.
가사. 그래서 숨을 쉬를 쉬어 가사. 땡유 톡제. 가. 어디?
So,
Okay. Right, so you-
so in Buddhist analysis of matter, also categories are made of different types of matter.
Yes,
Things that are tangible and has special extension, things that are not tangible, but still part of the matter. So there are different kind of material objects are identified, yeah.
I see. Okay. So what we do chemically, this is chemists are doing, by changing the stoichiometry. What they're doing is that it's to replace that chemistry. However, the physics to see it, the effect is that one electron is being taken out. If one bearing go into the lanthanum side, then one electron is taken out. Or one oxygen put in, add onto this original empty oxygen place, then one electron is taken out. So I'm moving out one electron. And the beauty of this is, if I have an empty space, then stuff can move, because this thing can move here. Or this one can move.
가사.
So this room,
the design 지금 나로리아 그 electron 지금 뜨셔야나 그
그렇지.
electron. 그에서 사지 동바차 그러와. 동바차 되거나 아니 예외의 electron 되게 파서 요구 따야야. 거가 라든데
Yeah.
기본으로 벌써.
so this is the basic picture now. Most people agree for this material to have. Why? It become metal, okay? So this come with a very interesting for the past 30 years, a lot of work, and has this interesting so-called phase diagram. And here we are showing this is the number of dopant, or the number of electrons essentially, or the hole. Here we talk about the positive charge. And here's the temperature, okay? So you're coming from a very original insulating, has some magnetic features, state, and gradually become metal, and then down to this region is we call the superconducting region. And there are many rich phenomena. Well, you ask Professor Lee, he said, I don't understand at all yet. We don't understand. So this is the current work. We're trying to really understand the full spectrum. However, this all come from this very simple copper and oxygen feature. Very simple structure here. So this is how experimentalists are working very hard to understand today, even today. And luckily, well, here is the question, why there are so many competing orders in this simple copper oxygen-based high TC material. Okay? But very fortunately, nature is very kind to us. So in 2008, we found this interesting new material. Has similar feature is the iron, also the D transition metal, like copper, with the selenium. Selenium, the center column is oxygen, right? But it's the one layer here, and you continue stacking on, this material becomes superconductor. So it's very simple structure, okay? And it can have a relative high TC also. Up to date, we found 10 years now, then we know it can have close to 70 K transition temperature. And you can even make it into just single layer to make it superconducting. This is very, very intriguing, And so we have created a platform to better understand the origin, that because the simple structure, so we should be able to learn more. And it's interesting that it can have a very important application also, okay? So the last 10 years, we spent a lot of effort, and many people work on that. So there is some understanding concerning from high temperature down to low temperature when it becomes superconducting. And similarly, there's such a phase diagram predicted, or we proposed essentially, that similar to the, you will remember I just showed you for the copper base. And so the superconductivity in this iron selenide is similar to the high Tc copper oxide, which is a result from a strong electron-electron correlation, okay? And as I show here, there are many competing orders, competing state, again, to get to this result. And now the question is, what is this? Do we understand, especially from a more realistic point of view, as experimentally, I like to see what kind of material, what possible to lead this. Okay, so we have done some more detailed work. Okay, this is a beautiful single crystal, very fine wire, and we examine that by electron microscope. Okay, and then to look at the structure, the diffraction, and also the composition of this material for the iron selenide. And we identified this quite interesting. The ratio between selenium and iron is 5:4, which means that 4 iron with 5 selenium. But if you look at the original picture I showed you, it should be 1:1. Ideally, it should be 1:1, but why this is 5:4? And that gives you this very, I don't know why suddenly it goes this. Anyway. Okay. Well, it gives you a very interesting, beautiful superstructure, from the X-ray and the electron diffraction. So we were able to use some very simple analysis to try to pin down why the diffraction is, in addition to those bright spots, there are some beautiful small spots. What is this? Okay, and the analysis tells us, if I look at the plane of the iron sitting on, right? So every 4 iron, then there's 1 missing. It's go periodically. Okay, this is only 1 cell, but you can see it's periodical. So this kind of iron beacon become a very older state in this particular 4 to 5 composition, which means we have 2 different iron sites. One is occupied, we call it sitting eye. Another site called a 4D site, which is empty. And this material is insulator, just like the yttrium 123 with 6.5 oxygen. It's not superconducting. It's not conducting at all. Well, I should not say it's just poor conductor. Okay? But this thing, if I add a little bit, just a little bit of actual iron, okay, gradually, and what happened is, this is 2 material. The up one is the one not superconducting, that is the insulator. But that bottom one picture is the superconductor. And here I show you is the X-ray picture, showing that where there is some diffraction peak going on. Okay, I just wanted to point out here the key feature. For a non-superconducting one, look at here. Okay, and we are probing this from room temperature, keep going up to a very high temperature. Suddenly, this peak shrink, right? Changing from this 2 position to that. Okay, so this is insulate the material. However, when it becomes superconducting, you see that the X-ray position doesn't move at all. Okay, this is the experimental data. I think for you, I think people know how we experimentalists are doing work. With this work, then we can do analysis and to see what the occupation of the atom. And then the conclusion is that, make it simple. The original empty 4D site will start to occupy by the iron atom. Okay, in this lower panel here. And we found out when you occupy and you make it more random, which means that I can use different way, okay? My higher temperature add more iron, more randomly, the material become better superconductor. Okay, so based on this structural study, we can conclude that these two sides, 16I and 40, which is empty, when it's older, is the insulator, okay? But when I have an extra iron atom or high temperature heat treated, become random, then the 4D sites still start to be occupied. And this occupation leads to electron, just like what I said earlier, taking out of the certain atom and give you the carrier. And here, we introduce that. So originally empty, now you start to feel, then you start to see the carrier. Okay, and superconductivity emerge from that. This is just like, so we are seeing this. We have two states in the system. One without, or is the empty, one with atom. Okay, these two states. At a certain point, you can just look like this, you have a domain world. I think in cosmology, using this picture to show this how universe form also, the Kibble mechanism. And we know if we can do much finer, when we have a very fine mixing, like this one, a lot of it mixing together the material, and I have a very good superconductor. Okay? So the key here, from our understanding today, especially from our own research study, okay, the material origin of this high TC, I can conclude this. Both copper-based and iron-based high-temperature superconductors, some form of defect, either oxygen non-stoichiometry in oxide or just iron vacancy in the iron-based material. And they both display similar phase diagrams showing that several very interesting physics state fitting to each other. And there seem to exist at least two different electronic states that necessary when you are properly doping. Either superconductor versus metallic, and there is a magnetic and non-magnetic. And we know Chinese, we always talk about this yin and yang, the coexistence. Is this the case? Probably more fundamental is that, as I say here, it's empty, then start to fill. Or here, it's filled, then it make it into empty. This is two analogies, but in that up here is the real state, real material. And here is the electronic, But that remind you, we have learned from Lao Tzu.
Lao Tzu.
Right? Lao Tzu, chapter 11, he said, 30 spoke meet at a half, because the whole we may use the wheel. Clay is molded into a vessel, because of the hollow we may use the cup. If we don't have this empty space, we cannot use that to hold anything. And the walls are built around a heart, because of the empty space we may use the house. Like this room, without this empty, we cannot sit in here, listen to your Highness the talk, right? So the conclusion is that tool come from what exists, but use from what does not. So that's the nature, right? It seems to play this beautiful consequence. So my question is a random occupation to the order empty space the most fundamental cause to novel effect in nature?
긴 사바
가서
중앙 사바 용에게 다 차긴 개치쇼디 아니 간다 지금 대왕기 아니 간다 또 동사 파동수 버지 it's the random occupation in the order's empty space 간다 대 고서요 와다 남가 델이야 아니 대왕기 고서심제
Yeah. So as we see from number 2, we need it empty and then start to put in, and then you see something beautiful coming out. Thank you very much. That's all my
Thank
talk.
you.
Yeah.
그런데 저 데리샤다는데 수다는 자외면 다는데 작자를 지도 구조다는 예버데 코로나랑 공을 전에 그 로그 교를 야부 제마토니네 그 나로게 제제때 주주 단계 동전망수보다 일렉트론 거보다 데 체인도가 아니 그 제다가라 아니야 로그 교를 야부 차동이 되는 것도 디자들이야 아니 두망 부초벽가야 두기 동자되기 돈에 내가 전부를 내기도 다 그런데죠.
Yeah. I think the question also, is this similar to what the middle way you're talking about now?
What?
The middle way,
Middle way, yeah.
is this similar to that concept?
나는 뒤진이 되죠. 과다 강도 로조세 그게 땡루고
나래.
아다지 차장도 좀 먹고 시작될 때도 와.
나래.
아니 제릭 맨날 돈에 차장 내가 맨날 연구 시작도 와.
나래.
저자가 나한테 로조야 그게 tumbe zero 제 직식체 민tumbe 제 직식체 그 남시 차장 개발래 애는 점리 장만에 제니야다 제다 점리 차를 쳐부에 서그 그 자리야 캐연하면은 애들은 남도 사들 여러분다
나래.
답은 드리게서 다연한 주기열이 애니 얘네만 돈들 사돈들 키우고 열이 다가는 시기다 민마 마스네 키우고 열어
나래.
this 자리야 mental 개연하면은
So His Holiness is just curious. It's just since we are talking about conductivity, so it's not necessarily directly related to superconductivity, but the basic fact is that some mediums are better at conducting electricity and some are not. So there seems to be objective differences between certain mediums. So, so within the mediums that are actually quite good at conducting electricity, since temperature seems to be a factor, especially with the superconductivity, can one say that the same medium, whether it is discovered in a hotter place versus in a colder place, will make a difference in the ability to conduct? And similarly, meteoroids, as well as now people are going to Mars, so you can bring rocks from Mars. Not from the moon, and then eventually from Mars we will have rocks. So will they have different conductive properties or any work done on this?
Yeah,
comparing?
actually, it's exactly the temperature effect. As Professor Lee already showed. For metal, it goes down. Okay, the conductivity will become better. Yeah, when the temperature lower, conductivity will become better. For insulator, it's go opposite way. It become even more difficult to conduct when you go to low temperature. So temperature does affect the conductivity of the material. Okay, and in terms of the different planet, where certainly because the formation may be different, and the different material where the conductivity will be different. Gold, silver, copper are good conductor, but lead is a very poor conductor compared with gold, silver. And what we are talking about here, metal is the alloy or compound, is the range can be very, very wide. Okay, but it's basically true. Temperature does affect that. Okay.
So what about meteoroids and other objects?
Well, meteorite with different material.
Yes.
A lot of meteorite have some iron metal, as I understand. Then the iron is the
Professor Lee. Oh, yes.
지사 편도 예배 제들이잖아. 다그도 다랑 저래.
So Solons was saying that if there are, especially really good material for superconductivity to be discovered in Moon, we need to go there.
Yeah, sure. Maybe we can find somewhere here. Right?
At least construct one big laboratory
Lab,
and carry some investigation.
research,
Could I make some comment?
Oh, yes.
These two are physicists, quantum physicists. I'm a chemist. I look at problem a little differently. So when Professor Lee talked about superconductivity, he talked about pairs of electron pairs.
착하셨어. 자,
And,
then to do
안에
no,
and then
말하자고
la.
Started. Let's start with the continuation of this discussion, Professor Lee.
I want to make some comment and try to connect two lectures together into one picture. Professor Lee did mention superconductivity, just like a pair of electrons, like a dancer dancing in the room. But Professor Maw-Kuen talked about is he seems to be building the dancing hall with the atoms molecule. And what I'm going to say is, let's imagine a dancing hall is three-dimensional. So with pair of electrons dancing in 3 dimensions. If Professor Wu were to build a dancing hall like copper and oxygen, all the electrons will tie up. So when this dancing hall was built, there's no electron, there's no dancer. So it's not conductive, there's no dancer. And so what you really need to do is to build a dancing hall with a little different structure. Like not if you're talking about like FESE, you have different mixture in such a way when you build the 3-dimensional dancing hall, there are some electrons left to pair up to become a dancer. So like doping some barium in the lanthanum or FES structure change a little bit. This is really building the dancing hall with some electron left to be a pair of dancer then dancing around. So these two things are really combined together into one picture.
Thank you.
그래서
但是古兰子松的你的大众们的话，你个段的松松是，这的背过当的这些就是啊，
또 도움이 가졌어요.
看到那种机理啊，个这些叫当你个段的来不了。
Shall I start? Okay. All right, so the next speaker doesn't need any introduction because it's me.
You need to introduce yourself, right?
All right, I'm from Duke University. So I'm going to share with you some work that I've done many years ago, and it's in quantum transport. So by transport, we mean pretty much what Professors Lee and Wu were talking about. We're going to put a potential difference between 2 points and try to measure the current carrying properties of that system. So it's quantum transport because you can only understand the behavior using quantum mechanics. So what I want to focus on are a few points, and hopefully this will, much of the audience has had a chance to hear about issues about quantum coherence and so forth. And hopefully I will reinforce that and tie everything together so that people can leave with a better sense of what all these terms mean and all these concepts mean. So I would present, well, now it's just going to be one experiment because I have more. It would have taken much too much time. So one experiment which exists with some key features of quantum systems. And these features are difficult to come to grasp in the classical context. So again, by classical, I mean what we're more familiar in our everyday life. So for this particular experiment, we're going to focus on quantum interference and also the Aronoff-Bohm effect. So this is a very special effect in which you can see physical. This is a very special effect that only occurs in quantum mechanics, where you can see the effect of a magnetic field even though your electrons do not move in the region of the magnetic field. Okay, so I want to start in more familiar territory, classical waves. So we're all familiar with, if you have a rope, you yank it a few times, you can see a wave moving down. So that's a classical mechanical wave. Another classical wave would be electromagnetic radiation that Professor Lin, for instance, talked about, the light shining down on us. And when there are many, many photons, it's more classical. So we're talking about that limit. So I apologize, I'm going to do a little bit of math, but I try to put as much physical intuition into it as possible. When you do a wave, it will oscillate up and down periodically. And that's often sinusoidal in its dependence. In addition to that, if you will see a drawing in a moment, and it will make more sense. So there are certain quantities that characterize a wave. One is how big the wave is. If you look at a wave in a pond, there's an amplitude. There's also something called a wavelength. What's the distance between two peaks? There's something called the period, which is the inverse of frequency, how often in time before it repeats itself. So that's shown here. So if you take a wave, sinusoidal wave, let's see, all right, where is the mouse? Oh, there it is, okay. If you take an instant in time, let's call it time equal to 0, and look at it along the string that you've shaken, you'll see it'll go up and down and up and down. The height gives you the amplitude. The distance between crests give you the wavelength. And if you did it differently, if you do it on time axis, instead of having distance here, you just look at one point and look at the thing go up and down. And time also looks like this. Now, the interesting thing is that if you have two sources, as shown here, if they generate the same type of sine waves, but starting at two different points, and they have this form, then they would be considered to be phase coherent. They will follow the same time dependence. But then when you put them together, you will see places where the amplitude is big and places where amplitude is small. So that's called interference. So the point is that if you add two waves together, you have a choice. This whole object here is called the phase, and there's this extra thing here that controls how shifted the two waves are. If the two waves are aligned together, when you add them, you get double. And if they're shifted by 180 degrees, they interfere destructively and you get nothing. That's something very unusual about waves. You get
초 지네요 초 지네요 군이 동거잡에나 지기 캔슬 단체 라메마 찬도 그래서 다들 랍고 그랑 그다 다르서
디 누시 좀 가르쳐 샤워. 니 너무 연두 찌기 매우 속이 사이디.
그
누가 좀 걸어 봐.
말다 인터페런스 레샤
가.
지기 동거잡샤 봐
저도 그 개방 계시도 누구만이 얘네들이 직계를 직파버. 디 같이 그래.
디케바 말다 군이가 캔슬 제샤래 니가 so when the interference phenomenon occurs both
당시 슈시 중에 말해.
waves cancel each other's out.
They cancel each other out if the phase difference is 180 degrees.
So will the difference in the force of the wave make a difference when they interfere with each other? I mean, one is a stronger wave, one is a...
If one is stronger than the other, the cancellation would not be perfect. It will just be reduced.
축체에 그 축충도 그랬어. 다고 축치는 직바에나 아니 네가 wave the map 차 두 그랬어. 다 지구 축체에나 아니 동거자변도 가고 축도 충도. 자원의 map 차가 많아서 나옴.
디 슈시 중도 가르쳐 하는 좀.
또 그지당
규진 여러 봐.
랑중 그 돈에 시에 거라. 그런 지당
규진 매버려.
말해 주jem 랑중 돈에 시에 되고 그래. 간다 납치 중 용በት. So you're talking about natural phenomena. In the natural phenomena, there are waves of different forces.
In fact, if you do this on the surface of a pond, have two sources that are in sync, in phase with each other, you would see regions where it's destructive, where they cancel each other, other regions where they add. You don't gain or lose any energy. It's just that depending on the phase difference, so to speak, you can either have construct or anything in between. Okay. So this doesn't happen with particles. With two particles, you can't cancel them. Well, we're not going into high energy physics, so where you have particle anticle. So, okay. So the really famous experiment started out using light. Okay. So it's the Young's double slit experiment. So there you take a light beam. It may work for short distance with this, but usually it's done with laser, because with laser, the phase is definite. You don't have randomization, the phase. You shine it through two little openings, so only light can go through the 2 points. Now you look at a screen far away, and you will see that the difference in the distance of the two paths, there's a difference in the distance it has to travel. When they travel different distances, the phase difference will be different. Then if you look along the screen, you will see places where the interference is constructive, so that they add. Other places it will be dark, or they destroy each other. So this is a wave phenomenon. And in fact, even with these waves, you see the separation on the right between the interference patterns. If you make the spacing between the slits smaller, make the spacing smaller, the interference actually separate out. And that is a form of the uncertainty principle. So in wave mechanics, you have uncertainty principle built into it. Now, the interesting...
Now,
Uncertainty.
the Heisenberg, the quantum knowledge, Heisenberg uncertainty principle says the DT casual Islam.
Now, the interesting thing is that what Planck and people like the Broglie, the proposition that a particle has a dual existence as a wave. You can do the same thing with the electrons. When you do it with the electrons, because the electrons are point-like, if you can do it so that you get 1 electron per second, you don't build up this interference pattern of dark, bright immediately. You get these random spots. But when you get many, many of them, you see this bright, dark pattern. So this shows that the electrons can behave wave-like.
Even when they are sent one at a time.
That's really hard to imagine. It interferes with the self. That's something that we all struggle with.
또 기지기지고 말해.
말에다나 그런 내가 들으시던데 다징엘 들라고 나버체제 무슨 되고요. 다다는 디 일렉트론 제제 일렉트론 레레 땅샤베네. 디 망부시다메나 고 뒤고 나버숙심부터 다 레레 주름 부땅베나니 오 글라고 남주르 태용도 스고다데.
또 럽스네. 뒤서봐.
또 간다 초원도 갈이야. 오늘은 진짜 이것도 담대 되고 정말 담대 그러면도 대 낙도 리모트 되는 거에서 말아. 그것도 리모트 되는 당대 되고 럽기 남주 되는데니지. So am I right in saying that if the wave-like features demonstrated when huge amount of electrons are accumulated, because we see this kind of bar-like pattern there.
Right.
Risha?
But as you already mentioned, even you're sending them one at a time, but somehow it knows how to interfere. If you try to find out which hole it goes through, try to find that out. You don't get the interference anymore. That's magical. Okay, so a little bit more math. Don't be scared of it. I just want to motivate. So during the discussion, it's not going to be scary at all. The thing that I want to point out. So here's h bar, which is the Planck constant divided by 2 pi. So we know this is quantum mechanics, famous Schrödinger equation. There's an I here. What is I? I is an imaginary number. It's the square root of -1. We usually don't know how to take the square root of a negative number, so we have to imagine something. Let's call it imaginary. I didn't invent it, but that's an appropriate name. So this makes it very, very different. This also is a kind of wavy equation. So using this, you can describe quantum mechanically a particle with mass. In the non-relativistic limit, this is what things look like. And the upshot of it is that there's something called a wave function. So this is like the sign that I have written before for classical wave. But there's a key difference in addition to the introduction of the imaginary. That is, the interpretation of psi is so-called a probability amplitude. It's not the probability, it's the probability amplitude. So you...
단은 고쳐 맞선 하는데 단은 quantum 거든 레시 자연도 갈때 넘버디 가다 독소 체제 imaginary number 속으로 해서 디 레시 자연도 단은 순한 거디 probability 세바치고요 말해서 probability amplitude 세지 봤다는 왜야 랍드 체온도 랍 도면 가져 바로만 볼게 디 amplitude 그 probability 전달해서.
So in the case of classical wave, the amplitude you can see, you can measure. Here, the probability is what you can measure. You cannot measure the amplitude.
The amplitude itself.
So, okay. Now we also heard about linear superposition. This is a concept. That means that if you have two functions psi that satisfy the equation I just shown, which we're not going to worry about, then if you make any linear combination, so add up some number, which can be not just real or imaginary, can be complex number times the first wave function plus another complex number times the second wave function, that's also going to work. That's linear superposition. It only involves the first power of psi. That's why it's linear. This is extremely important for physical processes, that it's a linear relationship. One last thing, because this is probability, when you square so-called psi, and add up all the probability everywhere, you have to get 1. You can't get anything less or more than 1 if you add it up everywhere. So because these are waves, and the consequence of all this is that you can have interference even for particles, not just.
가르쳐.
다나디
뒤처럼 뒤처럼.
가다 데이터 구조 데이터네 게지 되셔 잡은도 갈라 아니 로드 electron in kuran dugi rashi ine tele ya lab kan nam ju turn to ya de jab tu yo resam de sha.
Okay, so another equation, but no worries. So one way of formulating quantum mechanics is called Feynman path integral. And all you need to worry about is that it can be written in this complex form. It's exponential, the imaginary constant, times something called the action. Now, this thing may look scary, but it's actually made up of the sines and cosines. And if you take, and the reason I want to motivate this is that now if you look at the different paths and use your superposition principle, then you would have one action along one path, another action along another path. You have these two exponentials, then you add them up together. That gives you the new wave function. But to measure something, you have to find the probability of that wave function, and you have to square it.
David Bohm's 그래.
David Bohm.
그죠?
Okay, so
That's a photo of David Bohm there.
that is, yes. And I understand you have had many conversations with.
Oh yes, I consider him my teacher about quantum physics. He explained about quantum physics to a person hopeless.
Partly because
When I listen, it seems I understand something. After that lesson, nothing. David Bohm and von Weizsäcker, the German professor. These two, very kind to me.
So these two great physicists were the ones who recognized that if you put a magnetic field in between these two paths, but not where the electron may go, because the electron has a charge, it will have a way of sensing this magnetic field. In fact, it will introduce a difference. So the way I've drawn, the two paths have the same length, but by putting a magnetic field, you can change the effective path length. And it's written quantum mechanically in this form, but in the end, actually more relevant is that this path difference is going to be the magnetic field times the area of the magnetic field. So that, if you multiply the strength of the magnetic field there times that area, that will give you a measure of the difference in phase. Therefore, now by tuning the magnetic field, you can tune it from constructive interference to destructive interference. You can make it 180 degrees out of phase or 360, which is the same as 0, because these functions are periodic.
랍니게 대외고리야 다고저 체리가 돈에 제바 제투가 다고 랍니 투용도가 지기지리야 tum바제제 랍잡단 거 돈에 랍처로에 지다야 초 도조제제 지기지리야 캔슬 제야 두드리고 개주듯이 잡단데 그 돈에 나는 보험 그때 시험해야 보충 그래서
Now, before I go on, I want to comment on the question of coherence that we talked about, and the question of why, or some understanding, we don't know whether it's fully settled, understanding why microscopically we need to describe things quantum mechanically, whereas we seem to live in a classical world. So this has something to do with so-called coherence. Now, what I did not mention about these two paths is that in addition to the phase difference depending on path I mentioned, there's also a time dependence. And if the time dependence is not maintained, if there's exchange of energy, that time dependence would oscillate and jitter. And when you do that, the two interference will jitter. So you will average between sometimes destructive and sometimes constructive. And when you do a measurement on a long enough time scale, it would average out. So the interference will be washed out in that case. So then you don't see quantum mechanical effect. So that's the idea of the decoherence.
Quantum mechanical ke sometimes nega jikdi tanda kasang kami chungana shingi duden tamun nega blia duden penje jigil dewa huchim bache yondugala coherenceech chagor bas tene raben nega blia coherence de meba chayagi game of yours that tresha.
So as far as I know, and though my colleagues may correct me or feel otherwise, the only macroscopic phase coherence system we know are superconductors. Others are we're not quantum mechanical because when you have many particles, it's very easy to lose coherence. And this is one of the themes that Michael Berry has talked about repeatedly. Okay, so hopefully I've gotten people a better grounding in terms of interference and wave functions and coherence and so forth, and superposition. So I want to show some experimental realizations of these things. This is data from IBM. Richard Webb was the lead author, a colleague of mine. If you make a tiny ring, I don't quite remember what this dimension is. It's probably about a micron across or thereabouts. A micron is 1/100th the thickness of your hair. If you take your hair and cut it into 100 parts,
Tai tumbu jala da chungse shi.
그 숙신식으로 만들어.
그래서 시식을 단데 ring lam. 이네다 충중 타무 쉬우지. 따지기 tumbu jala da 자자지기 소리처럼.
and then he put a magnetic field perpendicular to the view graph. So now you have a magnetic field in this whole region, and then you measure the resistance as you pass current between the top and bottom and change the magnetic field. Now you see you're tuning the interference phase and you're getting the quantum interference. So this is a solid state realization of the Aharonov-Bohm effect.
experiment ke tone. Kunjo experiment ke tone namkyut ten to quantum interference is the.
Now you can also do it in semiconductors. My colleague Greg Timp and myself were the first to do in a semiconductor. And this is also kind of interesting. Quantum mechanically, we live in a three-dimensional world. And classically, we cannot really get to two-dimension, one dimension, because we would think that to be in two-dimension, one of the dimensions has to be shrunk to zero. And it's very hard to make something that shrinks to zero. But quantum mechanically, you can do it, because when you shrink a dimension, the quantum energies become very, very far separated. And if you get so high in energy, you don't have an energy to access it, then you're locked into the lowest state in that direction. And that's how you get to two dimensions.
그3 dimension스에 가래.
Then ngara
4 dimension 유효로 그리네.
나래. 단단 들으셔야 단디 ngara 단다 규매 냠용 또는 제인도 그 3-dimensional world 나 여러봐. ngara 규매 냠용 되게.
그 초시 그리네 요로.
총시디 초계지 말해.
맞다. dimension.
라레.
뭐 맨날 요로.
라레. But you know, for example, even when you
뭔가
shrink,
3 dimension 서과도 가이나 좀 세.
so can you explain a little bit more clearly the 3 dimension and the 2 dimensions that you're bringing up here?
Sure. So imagine, let's just take a picture past that. Thank you. So to us, this is a very thin thing. Even though it's thin, it's still three-dimensional. It has a finite thickness, right? That's not zero. The thickness is not zero. That's still three-dimensional. But quantum mechanically, when you're thin, the wave function, so Planck is the one who says that the energy allowed states are discrete in their energy. So it's not like you have any energy. And when you make it very thin, these energies become very, very far separated.
So I mean, even the notion of thinness is a relative.
Pardon me?
Even the notion of thinness is a relative concept, isn't it? Thinness.
Thinness,
Yeah.
thinness, yes.
So that's a relative concept. So you have to be in relation to something.
Exactly. Right, exactly. Right. So for instance, this is actually something that Professor Lee has much more expertise. When people talk about extra dimensions in field theory, why we don't see the other direction, dimensions, why we only see three dimensions, it's because the extra dimensions are so small that in order to get to the higher energy states to see the dynamics, you have to be at the Planck scale, which is 10 to the 16th giga electron volts, which is very, very high energy, and we cannot access it. That's why we only see three dimensions instead of 10 or whatever. We don't really know, but that's one of the postulates. It would have been easier to explain if I hadn't gotten rid of all the other view graphs, because there was one in there. But we can discuss more later. Okay. So now we have this semiconductor system.
The Ting-Kuo ready to get the 2 dimensions like that. Ting-Kuo ready or ready Ting-Kuo the 2 dimensions, the 3 dimensions like the Leland. Then also now.
Okay, I'm running long. Okay, in this semiconductor, there's a 2-dimensional electron in this layer. So I can't draw a 3-dimensional system, but this is when you're looking, if you look this way, you're looking down at this. So parallel to the top interface, there's a 2-dimensional sheet. And if you pattern it, you get a ring here. And then you can do your Aharonov-Bohm effect, and those are some of the data that we had way back in. Oh, the left is Richard Webb's, and the right was our data in 1987. Okay, so I want to change gears now. I'm going to make use of all these concepts that we talked about to see a different phenomenon. I'm going to talk about chaos a little bit. Chaos is something which is deterministic. It's not random. What do I mean by chaos? It means that I have a rule that tells me where, if I know the particle at this point, at this time, and its speed, I can predict its position at the next time. So it's deterministic. But if you take a particle and put it in a confinement that looks like a stadium, so what do I mean by stadium? So these are stadiums. It looks like a football stadium. Then it turns out that if you have a particle, even though you may say to yourself, okay, there are trajectories. If you bounce perpendicular back and forth, at some points, it should just keep doing that back and forth. That's very unstable. If you're just a little bit off, it gets into a mess, something like this. The thing would just bounce all over the place. So if you're a little bit off and you're very far away, that's a sign of chaos. So a very well-known example is called the butterfly effect, where if you look at weather, the supposition is that a butterfly in Brazil flapping its wings could cause Texas to have a hurricane.
가르치는
라
조유야 되게
디기토는 텍사스리아 하리케니 와야기
가
야 텍사스리아 단데 룽 하리케니 와야기 겐체 인시베스 랍고레슬람.
Okay, so now we have a problem. The supposition of chaos is that you're extremely sensitive to initial condition. If your initial condition is just slightly different, you can be far, far away. Quantum mechanics, on the other hand, tells us there's the uncertainty principle. I cannot define something very precisely, so how can I tell if two things are really slightly far apart? But no matter, even though you can't really define it, you can see consequences. So what we're going to do is look at the difference between two different cavities. One is the stadium cavity, which is chaotic. We're going to open two little holes on two ends so we can pass current and measure the resistance through it. We're going to differentiate that from the circle cavity, which is not chaotic. So this circle cavity has symmetry, so it has quantum numbers and has stable orbits. So they have very different behaviors. And you can see if I measure the resistance by changing the magnetic field that I pass through the plane, this shape looks very different from that shape. And these shape differences are related to the Aronoff-Bohm effect. Okay, so here, unlike the rings, I don't have a well-defined path, but I have many different paths corresponding to the classical trajectories. And each trajectory will enclose its own area. So if we go back and look at the phase difference between two paths to be proportional, to be equal to the magnetic field times the area, these different paths will have different phase differences. And you add them up, you will see the difference in shape. And if you want to be more quantitative, it has to do with the distribution of areas. In a stadium, because it's chaotic, it has a single well-defined escape time. So the distribution of enclosed areas is exponential. In the circle, there's no single time scale. The distribution is power law. And now we go back one more step. The relationship between area and magnetic field is sort of like the uncertainty principle. They're related by something called the Fourier transform. If you Fourier transform an exponential, you get a Lorentzian. And if you Fourier transform certain power law behavior, you get this very sharp triangle. So now we have an example where putting all these concepts together, we can differentiate between two types of system, one that is chaotic and one that is non-chaotic. And the sad thing for me, or maybe not so sad, is that I've been told that this data is in a textbook. Although, unfortunately, they didn't refer to me. So recently I gave a talk and people in the audience, my colleagues, oh, I've seen that. These are people from Germany. Oh, I've seen that in the textbook. I didn't know that that's your data. But anyway, it's all a good cause for science.
디 툰데 디 치스타나 디 퀀텀 피지ክ스 텍스트북 나 요레사 담제 제베가블야 녜녜조 멘디 텍스트북 나 통주스라고도스 디 텍스트북 나를 크라밍 디 큐어 사마레사.
So I will conclude by asking His Holiness a question. So we just saw that in quantum mechanics, we can have effect even though we are not going through the region where there's a magnetic field. So something which is not in the region where the electrons are can have an effect. What are your thoughts? Are there examples of something similar in the Buddhist teaching and philosophy?
가서 계속 가려다. 가서 이마 가려.
니가 이제 무슨 어때요?
말면 말해. 다 희화게면도 가다가 I think ancient Indian tradition. You know, all destructive emotions such as anger, jealousy, these very much related with ignorance. Ignorance here means we totally sort of relying the appearances. So since you see the 가져다가 낭수 가리고 코랑을 담발지 이지 시대 되기 취미지 남도 돼야지 차용고 요 유자네 다더 가서 어때만 있어야 돼. 저상은 능수점으로 참아샤오시네. 고래 일루로 잡으셔야 돼. 다 대학에다 주율되어야 돼.
So this relates to some conversation that we had yesterday, which in the Indian tradition, the classical Indian tradition, the idea of two truths, two levels of reality is brought up because a large part of the problems that has to do with our emotions, strong emotions, really comes from a kind of a naive realism which believes in the world of appearance, the world of appearances. So, however, what we perceive does not completely correspond to what is actually the case. So therefore, a distinction is drawn between two levels of reality. One is the conventional, everyday perception. The other one is the deeper, underlying, ultimate truth.
Every day is asking. 도만이도 every day 도와도와. 가다 맞아면 가네.
So it's an unexamined perspective on the world is the conventional truth.
Therefore, according to Indian tradition, is the investigation of the reality. They we call the understanding about reality that we call wisdom, jnana. That is the counterforce to those illusions. Like that. So now, what is the reality? Now then, many different schools of thought. So the quantum physics clearly shows these big differences, appearances, and reality. 당연하다. 치숙진 그거를 또 quantum physics 판도셔도가 나왔다도 좀 해도지 쉽습니다.
So one thing that's for sure is that the more you expose yourself to the quantum description of the world, it makes it very clear that there is a huge gap between our everyday perception of the world, naive perception of the world, and actual world of physical reality.
세상 가정 계주들이 quantum physics 직배되게 배심을 띵ning 예버 톱딩했들 차단 걸로 아태근지 못 숙충하사지.
So therefore, yesterday we talked about this Chinese quantum physicist making the point that in some quantum physicists who genuinely live with this kind of view of the world, physical world, maybe there is less tendency to grasp at black and white and in strong terms in objective reality.
So 또 다들 자리 있나다. 다들 자리는 전 이해하면 되지. 낭좀 테임 심벌. 다들 자리 있나? 가게 이해하면 되지. 상고를 주기 우머지잖아 나야. 수중어부 명점실 나가야 하는 명점모스. 중미수도 갈라시 티실 명점 이야매.
So one thing that Nagarjuna pointed out very early is that however, even though we have this conception of reality, but if you subject, anything to critical analysis, trying to find exactly what it is that we are pointing our finger at, then nothing could be found. Nothing can withstand that kind of analysis. So he says that, for example, with relation to matter, in the Buddhist classical theory, matter is composed of 4 elements. So they're without the elements.
중어도 니스체니 중어디 규체 중주 남중가서 속졌어야 지라디디 중주체 지자다 계지기 규 중어거라 다들으나 니야면 이두잖아 델레 중어에 다 대준배서 올려다 대심하시는 용대베 중주디디 아니 다들으나 니야요 말았어 자다 매번 말봐 패는 적도가 되게 자동 발리세제 스부르 중어 다들으나 발리데 자다 아니 가서 우리 거기 침이하게 류다 다들 전 편이합니다. 그래서 마다 마지막 이제 들이 하셔도 연구도가 다 든지 인도 다 팬은 저기 아래 다들 전에 이야기야 말이 든지 인도 전에 다 마다 마저병 안에 아니 작배관에 지금 작배관에 다 캬라 빼야 오르시디. 그래서 다 되게 그 아테가 전부 콜네 탄핵의 자제들이 조심하. 애를 하고도 있고 때는 좀 시행되잖아요. 우면슝네 댄진 좀 좋은 거 댄진 동반이도 시 댄은 댄에다 와디. 드니 우면 나오는 것은 손셔야 되기 탄핵을 써야 돼. 쉬우진 거 좀 모르셔. 저들이 인도 다디 테오리게 지고 말다. These are not only just the theory.
So in this, Nagarjuna is commenting within the context of classical Indian theory of matter, where there is an understanding that ultimate constitutive elements are really those elements, and the macroscopic world of matter that we experience are derivatives, basically composed from these ultimate constituents. So when you subject even the elements themselves to critical analysis, nothing is to be found. So if the constitutive elements themselves are not to be found, then how can you find that which is constituted from that? But then he goes on to say that, but that doesn't mean to say that the material world does not exist. We just had a cup of tea, we had nice, cakes and stuff, and we also experience satiation, the sense of satisfaction having enjoyed them. And also if we were to, bump into this table, we're going to knock it. So there is an experience, there is a world. But so in this way, the notion of two truths is brought up so that while you acknowledge that in the ultimate sense, we may never be able to, describe what it is we may never find anything that can withstand that kind of analysis, but that awareness does not undermine your appreciation of the robustness of the lived world that is there. And also the one advantage of that is that this really helps the way in which we relate to the world, because if we are aware that the solidity and the concreteness that we perceive is our own perception, not the reality, then it will have a tendency to undermine strong reactivity and strong responses to them, so which then also help our relation to the world. So His Holiness was saying that this looks like a really good middle way, and therefore Nagarjuna has said in his fundamental treatise on the middle way that that which is dependently originated, so because he's really now, in the end, you can talk about the world and reality only in terms of relations, only in terms of dependence. So then he goes on to say that that which is dependently originated is essentially empty. And this, is a world that is dependently designated, because when you use identity, you have to give them designations. And this, therefore, is the middle way. So you don't reject, you don't go into nihilism, nor you go into, absolutism.
저런 quantum physics 양조다 특히 파센 유진이 근데 주면 zen도 산에다 니별 차윤도다 때는 따고서 양조 되셔버다.
So since what quantum insights from quantum physics is suggesting is that the objective world that we tend to believe in the classical sense really don't stand up. You cannot find it. So then, but at the same time, you do need to talk about the world. You do need to have a description of the world. So maybe quantum physics can borrow more of the Buddhist language of this dependence, this relational kind of, approach.
certainly 인도 간다 나한테 서 quantum physics 가게 요마르스 그 이지 제딩인데 강주지나 샤샤 자해 먹어체 칼라이 먹어체 샤샤나 타냐 이거지 영어의 소리고다.
He's also saying that there are sometimes you do meet some quantum physicists who even question the notion of reality because of their insights that they have gained. So he was saying that he thought that how about putting such people in a room without any food and without any tea and see if they can feel the effect of reality.
자자가 루루기 다직 삼삼부터 되게야 지 딱도 잘 많이 버는 고래간에 도스체니 지도 요마르스 시고 버다 타 루루기 댄지를 뭐 좋은 거 되는 동반이도 시에서 딱 되게 슬lum차들이 디셰도 쉬우는 것이 그러셔 동반이 있다와디 아니 댄중기 대권이 있어 다 독스타임도 와 쉬우는 것이 그러셔.
So the Nagarjuna's view is very powerful because in Buddhist history of Buddhist thinking, there have been different types of approaches, including a particular strand of thinking, the mind-only school, that went to the extreme of actually rejecting the reality of external world. And so Nagarjuna found a middle way where he accepts on the conventional level the external world just as our internal world of experience. So Nagarjuna's approach really seemed to be very powerful and insightful. And when it comes to positively characterizing the reality description, he uses the language of dependent origination, the language of emphasizes the language of relationships.
저장 아까 대저도 붙임도 덩굴되는 인다리 삼단되게 식권대 전화 멀려봐 나랑 게 섬기 딱 봤어 섬대야 땅나 갱가제 내루징고 에모 또한칼라 춘진 땡버시 다 디강도 섬지도 샤위나 또한칼라 춘진 땡버시 인랑섬 예면 나오로 녀나 거 저거 멀려도 아니 나게면 나가 난 저거 시시에 뭐저 준부치 낭자고 규면 때모도 냠가와 낭도 송주디 루미기 때진 게 뭐니
So His Holiness' point is that actually this is not just a speculative philosophy. It has real application for a Buddhist practitioner to really internalize that way of perceiving the world.
Buddhist practitioner and Buddhist also the general, particularly the student of Nonlinear tradition and the follower of Nagarjuna's Longsu Pusa's philosophy.
So he was given the example in his own personal life. On a daily basis, he uses a beautiful experiential song of the 7 Dalai Lama, which really encapsulates in a poetic way how to internalize this insight into emptiness on a daily basis.
We need to move on, so we'll hold a discussion after the next talk. Thank you so much. Okay, so let's move on to the next talk. Professor Mo Chung-Yuan from Taiwan University. He's also a member. Thank you. Yeah, he's also an academician. He will be giving us a talk about something familiar and also unfamiliar: water.
Water.
Suppose I'm giving him empty glass. 추해.
Okay, Your Holiness and fellow follower, friends, it's my great honor to be able to speak here on a subject very familiar to you as water. And just when I start to talk, heaven sent down a lot of water.
Oh, yes.
I think heaven agrees with me. And I also want to promise you that my talk will be much, much more easier to understand. There's no quantum physics. I'm not physics, I'm a chemist. So the subject of water can be taught in many, many different ways. It is also an important element in Buddhism. One of the four fundamental elements, water, fire, wind, and earth. So there are other people also very concerned with water. There's so much water shortage, water resource shortage in the world, like in Africa, in desert place, also in India. Many people are concerned. What I'm trying to do is to give a scientific view of water and then relate to the two great concerns. We have one, the point of view of Buddhism, how you look at about water and how it can be integrated with the scientific view of water. And the other is the natural water resource problem, which Professor Lee tomorrow may touch in a great scale. Okay, first, water is very important to us. It's life-supporting. Our body is 60% of water. A newborn baby actually has about 70% water. But water is very peculiar. It's unusual liquid in the sense that it's probably different from most of all other liquid we know. So it's special, but I would not call it miraculous. It sounds more like something religious, but the water, it's just very unusual. I will show you how unusual it is. Well, if you look at the abundance of chemical elements in the universe, we have something like 109 chemical elements. You start with hydrogen. That's number one element. Number two is helium. Okay, they are the most abundant elements in the universe. Helium. And number three is oxygen, okay, in the universe. But helium does not have any chemical reaction. So if you consider the most abundant chemical reaction resulting in molecules, you can you would believe that should be between hydrogen and the oxygen, which give you water. So you probably can agree with me that the water molecule is the most abundant molecule in the universe. Actually, people, scientists, astronomers, has been able to detect water far, far, far away in the distance of 11.1 billion light years away from us. And that's the signal which people decide is coming from water molecule. And it's far away in the galaxy, and so that you can believe that it's all over full in the universe. On Earth,
The galaxy is the Shih.
okay, let's talk about the property of water. In school and in daily life, you know what water is. It's shapeless, it's formless, it's tasteless, it's odorless, it's colorless. All is a negative term. So,
추두 처음 숙제 말해.
But the water molecules themselves are material, though, matter.
Yes, yes,
네.
yes,
네.
yes.
네.
But the water you pour in the glass,
규마 쓰고
it looks like nothing to you. I mean, it has no shape, no form, no taste, no odor. Of course, scientists look at water in a lot of all kinds of property that's influenced by temperature. Since 19th century, chemists has developed a robust framework to describe all liquids, like ethanol, methanol, or all kinds of liquid, and predict what they're like. But the water seems to break all the rules, It's peculiar. It's the most abundant liquid, but surprisingly, it's scientifically it's difficult to understand. It breaks rules.
그냥 창마도 줄이서가 주말에서가
So would you say, ice is water or no?
Ice is solid water.
Solid water.
solid water.
Solid water. Okay.
So this only is getting to the point. It's not formless.
And vapor is gas water.
가서
I guess it's
And the vapor, the gas water.
okay. And in the air, we have lots of gas water. Yeah. How water is peculiar, how we call anomalous. Its behavior differs from the normal liquid. Most liquid, when you press it hard, it would not like to flow because it got squeezed and does not flow. But water behaves in contradictory. When you press the water, it's easier to flow. The water actually becomes more easy to flow. Second, most of the material, when you heat it, it expands. When you cool it, it shrink in volume. But in water, in certain temperature range, water, when you cool it, it expands. So that's very unusual. And solid water is, Your Holiness just mentioned, that's ice. It's lighter than liquid. That's also in contradictory to all the other liquid. When most liquid, when you solidify, when you freeze it, it sinks to the bottom. But for water, it flows. That's the ice. It floats on top of water. And water has a density maximum, and also, I would say, density minimum, which we discover. Most liquid, when you change the temperature, its density just continues, and no maximum, no minimum. Just change it a little bit. But water behaves very drastically. And for such low molecular weight, water is very light compared to other material. It's very light, but water is a liquid. Otherwise, in other stem molecule type, it should be a gas. It should have been a gas, but somehow it becomes liquid. And number 6, water has very high surface tension. Just like the picture shows this insect, and it can stand on top of water. On other liquids, the insect will just fall inside. It cannot stand. This phenomenon is due to high surface tension.
창마도
말에
향되고
잡아 말할 때 줄에.
향
주간에
알레고 추조대
use this.
양모인들도
나래.
슈퍼를
나래. Then
산에 차시 보러
the
Okay.
liquid 현다에나 근데 못 맞템도 그러사. So you're saying that if it's not water but other types of liquid, this bug would just sink.
We think. Yeah, but water is different. The solid water.
근데 차를 줄에 말해
But what about tea? Tea is water, yeah?
Tea is essentially water.
Yeah.
When you freeze it, the rock,
표지 벙구디가
the
퍼그리
ice
Yeah.
벙구디가 퍼그리지
So the flies can float on it, yeah?
Yeah.
Yeah.
Well, we're killed by the temperature. It's too hot.
차 타고 인자 안경이야. 차 타고 인자 그 세션.
It's too hot. Okay,
그 제세로 유로 독시로 유로
this is our study.
Someone was saying, it's a competition whether the heat of the tea is going to kill it or you're trying to get it out is going to kill it.
Yeah. This is our data about 4 years ago. We were able somehow to keep water from freezing down to very, very low temperature and measure the density of water. Density is weight divided by volume. So higher density means smaller volume, okay? And we measure the density as temperature change. I'm sorry, the x-axis in absolute temperature, so you have to subtract 273 to get Celsius. And you have maximum density at 4 degrees, as everybody learned in school. But then it goes down very quickly at low temperature, and reaching minus 50 degrees Celsius, you get a minimum density. That's very peculiar, because most other liquid will behave its behavior like this, just monotonic like this. And water turn around and go back. So if you look at this behavior, you almost think that there are two kinds of water. That is high density water here and very low density water here. It seems that water is more complex than you think. It consists of two kinds of water, high density water and low density water. Actually, just last year, a group found that indeed there are two kinds of water, at very low temperature. This remarkable property is that we find the water can exist at two different liquids at low temperature. Okay, and this is a discovery, very important. And in normal temperature, like room temperature, we of course have only one liquid water. But the fact you can have two different kinds of water at very low temperature implies at room temperature its structure is complex. It's kind of mixture of these two, and more complex than you think. Now I come to the molecular model of water. The water you see is macroscopic, but the microscopic consists of many H2O molecules. The H2 molecule are shown here like a banded stick. Okay, this is hydrogen, and this is oxygen. Oxygen is negative charge. The hydrogen is positive charge. So they attract each other to form a bond we call hydrogen bond. Hydrogen bond. This is hydrogen bond between two oxygens. That's why they want to stick together to form a complete structure. And for a central water molecule, H2O, here you have 4 hydrogen bonds to neighboring molecules. 4. Indeed, that's the structure in ice. And notice that this interaction picture is completely classical. You don't need quantum mechanics to do the rest. So I would say that the quantum mechanics somehow is not needed. Of course, the water molecule itself, the shape, is a consequence of quantum mechanics. But otherwise, when you look at water-water interaction, classical mechanics is enough. This is a picture of reductionism. We start to look at reductionism. From there on to go Macroscopic scale, no quantum mechanics. I'm sorry to tell the physicists. Oh, that's minor. That's minor. I consider minor. Yes, but when you look at the cold water cluster, then H2O itself is a consequence of quantum mechanics, but how they group together can really be simulated, computed by classical mechanics only. And this is how classical mechanical simulation of water liquid look like. It look chaotic, look random, but actually when you look closer on the left-hand side, that's closer, it has a structure just like ice, but it is more distorted and it's moving and they are not in permanent shape. Okay, so I was,
对吧？这属人工弄到浪子是吧？这对出对这对在的家的话做的，啊，
로를 착하고 싶다 디.
这样子下一位，这属人工弄到浪，驴个都是那绕去呢，这插水的这个对插子是吧？这个是关键，这个对的插水的些，等那出对些。
자도 다시 말해. 나래.
뒤처럼. 뒤자 적도도 추도 그럴 수가 있나? 추도를 적도 차와셔다.
나래.
가. 가자.
가르쳤어? Ale 나를 시에부터 좀 그자 명다오 뭐도
알레
제 코란에 더 미세게 아유스 지중 그 세제
알레
근데 직선에 저 정유 그 집에
알레
딜로 작하고 싶다. So his holiness is referring to classical Buddhist Abhidharma description of the how from the smallest kind of atomic level aggregation of molecules occur.
Yes,
in
that's what
in the Buddhist context.
yes,
So there
that's
are
what I'm discussing here.
Different names of different types of molecules are.
one Buddhist school of thought.
Yeah, this is in Abhidharma, now one Buddhist school of
Actually,
thought.
that's the correct modern view of liquid. And just a collection of molecules interact, they interact, move around. And on the right hand, this picture, if you just continue expand, connect together to 1 centimeter size, that's water describing. Okay. Now, my question, I have a question. How big a water droplet need to be to have a water property? Because individual water molecule is not a liquid water. Two is not. Two molecules stick together. Three, you don't have this water property. But when it gets bigger and bigger, you see water property. And then the question is, how big should it be? So I introduced scale here. From 0.1 nanometer, that's one angstrom in the left-hand side, all the way to 10 centimeter, okay? And this scale goes from atom, molecule, DNA, virus, bacteria, hair, ant to tennis ball. In this scale, that's the nano world, between 1 nanometer and 100 nanometer, that's the region I focus in. I look into that region. If the water is size of that size, the method is we put water in a very narrow slit, which size is in nanometer size, and do measurement of its melting point. And we find the melting point change as the size decreasing. When size decrease, it goes to the right of this graph. The melting point gets lower and lower until at this point, that's 1.6 nanometer. 1.6 nanometer is very small, where you no longer have freezing behavior at all, just liquid water, just So I would say about that range, water is no longer normal liquid, not like it. So give you a brief answer that is at 1.6 or 2 nanometer, you lost the macroscopic behavior of water. You should call it something else called water cluster. Okay. The next subject I want to bring up is that water is very accommodating. It's the most accommodating liquid. So in chemical term, we call it solvent. It dissolves many things. It brings things together. Just like your holiness, you bring everybody together. Bring everybody together.
근데 주디 가들 망부지 수 부서도 그랬어. 주고라 개주. 근데 근데 그 망부지 수 부서도 그랬나 보다.
So it dissolves sugar. It can dissolve when you make tea, you can put sugar. It dissolves water. It brings water in. It brings iron. It brings salt. It brings acid into water. It brings base into water. It can dissolve amino acid. It can dissolve protein. It can dissolve carbohydrates. It can dissolve, bring DNA, bring lipid. All are necessary for life. So that's the basic solvent for all the material you need in your body, in your life. It brings everything together. But when it brings everything together, somehow a strange thing happens. Out of formless, when you just a cup of water dissolve everything, it's still no form, no shape, no structure. But out of formless, it began to form. That's the life. Life is between form and formless. Okay, that's the thing I want now to discuss about. How can form occurs when you bring all this, everything together? They start to self-organize into structure, into life. I want to start with this point, that looking oil and water. Here is a cup, has both water and oil. Of course, you know that oil and water does not mix together. They don't mix together. They just separate into oil and water. Yeah. In that sense, oil is water hating. It hates water. We call hydrophobic. And sugar, like water. Sugar always like to go into water. Water loving. It's hydrophilic. So is salt. Salt like water also. So there are two kinds of molecules. One is hydrophobic, hate water, represented by oil. The other is hydrophilic. When they meet each other in a single molecule, that's lipid molecule. Lipid molecule represented by this model. This stick is hydrophobic. That's oil part. Lipid has lots of oil molecule on it. It's hate water. And its head is hydrophilic. Its chemical term called phosphate is ion. As I say, ion like go into water. So they have a dilemma now. Whether they want to go into water or not. Part of my body hate water. But on the other hand, this spherical head like water. So they form self-organized into this structure we call micelle.
So what is micelle?
Micelle is a collection of this molecule. Collection, they just collect each other and assemble. They self-assemble. You don't need a worker to help it. Because in that way, this water-hating part, that's hydrophobic part, hating water, they can avoid water. They just want to avoid water.
간다 제가 가실이야 개주니가 장드냐 농그 릭다고 지금 추년보 마데니다 야슈 지네다도 나시제 추년보 데니게 자연이가 장데 버들려나 안고 추년보 르연도 가라 코란조 to organize self-organize 제제
And of course, they can also self-organize into we call bilayer membrane. That's membrane, structure. Again, the water-hating part was inside, and the water-loving part is outside and facing water. Water is around on the outside. This kind of structure can form infinite in many different forms as in the biological cell. Biological cell, first, you look at it, it has a cell membrane. This is, on the left-hand side, this is cell membrane. That's formed by these lipids. It has hydrophobic and hydrophilic part, and they self-organize. So forms start to occur instead of structureless dissolution. And in a full cell, biological cell, you have many membranes, like here, there's a lot of membrane structure, like here it's called mitochondria, and there's a nucleus, nucleus of the cell. Again, on surface of nucleus, the nuclear membrane. So water drives the membrane formation.
추두식으로 해.
말에 단데 셀
아, 네.
셀 나로리아 다고 출이야 가외렉지다 다고랑 가외 다녀지도 출라만 가외렉 니가 창되게 얼어 창되고 고라야한테 디 캐주에 추도 dwi제 저거도 가는 거 소생 미그 거버럽지 두고 그랬어.
So the conclusion is that water not bring everybody together, but also it helps to organize into this.
추두사도 멤버스다.
나름 라운
아주 추두세로.
나름
추파비자지기 하시. 제가 추파비자지기.
나름 근데 제가 실이야 출로 가냐다 마가 니가 창되니 연구 그래서 디찬은 단데 biological 나로리아 수쟁 그 그거만 붙이 독스토고 그래서
Okay, that's one aspect of the water's role. It's self-organized, it's form into form of all the fundamental structure in the cell. The second role is in the biological cell, you need energy. You need energy. The energy we call chemical energy. Chemical energy. The fundamental chemical energy, of course, comes from sunlight. And this reaction tells you photosynthesis coming from sunlight in the plant. You have sunlight and you have chlorophyll. Chlorophyll is the catalyst that making this molecule. And you have CO2, carbon dioxide, and then water. Water, then after this photosynthetic reaction occurs, you store your sunlight energy into chemical energy in the form of sugar, or we call carbohydrate. Its formula is C6H12O6. But on the other hand, you can look at it as 6 carbon plus 6 water. So water stores chemical energy in sugar. So water has two roles. One, water is opposite to fat. So they separate into intricate biological structures. They drive the structure, as I just talked about. Then second, water is the medium of energy storage when light is converted into chemical energy in biological system. That's what I mean when I say water is all-encompassing. It brings everything together, helps it organize, helps it give energy, stored energy. That's the great organization medium for water's role. You organize the biological form. Now, to come to philosophy, this old saying by Lao Tzu, again, we're talking about Lao Tzu. This sentence is very simple. It says, the highest virtue is like water. Of course, you can interpret it in many different ways. But I would like to cite the Kung Fu master, Bruce Lee. It's a good interpretation of Lao Tzu's sentence, saying, highest virtue is like water. I read this sentence, say, you must be shapeless, formless, like water. When you pour water in the cup, it becomes a cup. When you pour water in the bottle, it becomes the bottle. When you pour water into a teapot, it becomes the teapot. Water can drip and it can penetrate because become like water, my friend. Actually, that's the essence of Chinese martial art. In the martial art, you don't attack directly, you don't hit, you yield. It flows and it yield. And that's what the water's role is. I just explained to you. It penetrates everything, brings everything together, and it flows and it organizes. It organizes things to have good chemical storage of energy, and it functions as a biological tissue. Next, I will also show this Chinese painting. This painter is famous, Zhang Daqian. I would not describe what it does, but don't you feel a strong feeling of water in here? Not just the river, but also the cloud, the median, the forest, everything is permeated by water. And that, in that sense, water permeates everything. It describes a sense of that. Finally, I will come to the problem of oil. We scientists, as we discussed yesterday, as His Holiness instructs us, we scientists should also think about the problem people face, to solve people's suffering. Many places in the world suffer from lack of drink water. In places like Africa, people have traveled great distance to bring water, and water is dirty. In India, it's extremely high water stress, and the degree of stress is colored by here. Along the region of New Delhi, and upper part, upper left part, is great stress. Groundwater or exhaust. I think in this place, the water is less problem because in mountain. But overall, India, there's water resource stress. People lack water, drinkable water, clean water. How we can do about it? This phenomenon, of course, has to do with global warming, which Professor YTD will talk about tomorrow. I don't have the time to explain it, but because the impact of global warming, the groundwater of India, Indo-Ganges plain it become more exhausted. What scientists can think about is how to solve the water problem by understanding water to bring more water from places you never use. For example, in arid area, in desert, can you bring water just from air? In air, there's lots of water vapor. Although it does not rain, but water is there. We are studying those things, try to bring water from vapor into liquid water so that it can be used. Of course, that's a way of also doing air conditioning also, which is our subject study. Finally, I will just leave a few questions here for discussion. I stop here. Thank you very much.
Your Holiness, your thoughts.
Second question: is it possible to have life without water? 这样子，抽出来了，life 也有这个没有这个。
So, in relation to the second question, from a scientific point of view, would you say things like rocks are alive?
It's all life.
They are alive inside rock, but it's in space where it has water. there are gapes inside rock, and there water. So on Earth, at least on Earth, life is impossible without water. You need to have water. You always need water. But in galaxy, I don't know, nobody knows. But presumably, I would believe that in the universe, also life depends on water.
맞으면 유한다. 용어 책임다 뒤짐 셰윤도 난가 롱메 추사 셰. 파 팀주전에 사추 메롱 난가스. 다 기비기디에서 용어 지원에 남시드식 저기요래. 실로 세미 변부 런시디디 난가 롱메 추사 사추 메롱 자자가 출전의 수된 용도가.
So in a classical Indian tradition, there is the idea of worlds coming into being from emptiness, empty space.
Talk about five elements.
Yeah,
everything
dissolving.
come from 5 elements. Then finally,
Also
the way dissolution
is also dissolving through the 5 elements. So when the world universe is being formed, it starts from the subtler, which is space, then air, and then...
That I usually use describing particle space.
Space, yeah.
Space particle. That's the basis, no beginning. So the previous galaxies disappear and remain empty. That means space particle. Space particle also is momentarily changing. Otherwise, it's impossible to develop any
the other evolution. So from the space, you have the wind, and then fire, and then water.
The fire side, the heat.
It's heat, yeah.
Heat.
And then water, and then earth. But when
water side is liquidity.
So it's more to do with liquidity and coherence, the one that keeps the cohesion, and then the earth. But when it dissolves, so it dissolves from the grosser, which is the earth, to water. So there seems to be a recognition in this way of imagining the world, where there is a recognition that water is subtler than earth element, but then it's grosser than the other ones.
Maybe that's the way this Earth, our own Earth, started.
Really?
Our own Earth.
The whole galaxy is
the planet Earth.
Limitless
started.
galaxies.
In galaxies, many places could happen.
You see, come,
this way.
disappear, according to the
This
5
process.
elements.
Yes,
5 elements.
yes.
This process.
Yes. In the beginning of this planet, probably out of space, bring everything together with water and earth, and then energy, heat, to form this planet. I'm almost sure that we believe same thing happening in other planets, many other planets.
그래서 I think Big Bang theory. I think the concept Big Bang. 시즌은 딱 견해. 다 매버질 리그도 와.
So
딱 돼야 용왕한테 용당을 세우이나 아는 가서 용왕한테 펠와 디버 딘디시에 야구에 버서도.
So, of course, from the modern cosmology point of view, you invoke the notion of a starting point, which is Big Bang. And then from the Buddhist point of view, from that empty kind of space state, then the evolution of the elements.
Right, yes.
Yeah.
그래서 Big Bang 들도 와.
Yeah. And Big Bang concept could be accommodated and incorporated into
that
that process.
용 나도 되는 용도에 나한테 나걸 너무 추사.
So then you have this idea of a Big Bang, and from which the space and then the other elements emerge.
디지털이 빅방 가르쳐 준 버스라나. 내가 렐레용도.
So from that point of view, if the question is asked, where does the Big Bang come from? So at least for the Buddhists, there's something to say.
What does Buddhism say about Big Bang?
스페이스 파티클 예요로 봐.
Because there's never a period when there is no vacuum, there is no space particles. So new universe forms out of that space particles.
Space particle also you see the nature of changing, momentarily changing. So the different space particle combine, then energy come.
Come down.
Energy develop heat. Heat develop liquid. Liquid develop solid. So there's quite a logical sort of explanation. And the chakvek, you know, tango in the tongbekeva, then a chakvekeva, then in the nevekeva. That never said it is a ragwe on the chan. The travel on the chana gives me in the jibber, Gigi Tunyamarota. Ragwe on the shay in the nevekeva, then a jikvekeva, then a tongbekeva.
So then the whole process goes
The
through cycles.
Zamni Chawa Chaja. And they are the Tangachi of Kasa. Ka. Or Roger Jazo. You said sharing the Jutan with you.
So there's in the Buddhist text, there's actually quite a large scale systems brought in terms of the evolution of the cosmos. And not only through the five elements, but there is also a recognition of stages. So for example, there is the period of emptiness. Then there is a period of formation. Then there is a period of endurance or abiding. So it's the period of emptiness is the period when the previous universe has come to an end. Then there is a period of formation, period of endurance, and then there is a period of stage of destruction, which then moves back to the stage of emptiness, and then the whole cycle begins. And not only is it explained in terms of our world system, but in this text there is also a conception of limitless universe systems, all of which go through similar cycles of stages.
개발 민식 춘지 한가를 담아 놓고 지고 있어 말해. 매일도 추 가서 지선데. 다 민식의 배지 이거 가서 저기서도. 자, 님의 죄의 숙소지 철치. 도선 그래. 딩죽 차를 같이 해야 줘. 봐. 딩죽을 봐. 저다 뒤에 천이 투버다. 도 사이에 있는 저물이 그리글다 감드라지. 도스다 민지세도 다다 요소스도.
And then the destruction, what leads to the destruction of a particular world system, it's explained in terms of the function of the elements. So there are forms of destruction caused by heat or fire. And for example, the text speaks in terms of the sun, our sun, expanding in its, force up to the point of sevenfold force, and the world will come to an end through heat. And then there is also periods when it will come to an end through wind or water and so on. So there is a understanding not only of the processes, but also what would lead to the destruction. So thinking of global warming, maybe these texts are actually telling us something, that maybe the heat is where we are heading.
But no need to worry. Our generation. I think these after several centuries. Okay.
The way sun is expanding, it takes about. The way sun is expanding at the present rate, it will take 4.5 billion years before the sun will reach the earth. At that time, we will all disappear. But it's 4.5 billion years from now.
가자. 너무 좋은 질문이세요.
말이 철로스. 철로스. 자본인 토엘이야 4 billion.
True.
로지고
True.
그래서
Now here, this is still to say, I also not very clear. Many years ago, in Switzerland, what called this CERN or something? CERN.
Yeah.
CERN.
Yeah.
There I met, I remember, 2 Italian scientists. I learned first time quarks. Quark number 1, number 2, number 3, number 4, not very clear. So that Italian scientist, he mentioned the Big Bang, 12 billion
Years ago.
I remember his face. He mentioned that.
Very intently.
Then one occasion in Bombay, one American astronomer, he speak, and he mentioned 25 billions of years. So then I thought maybe between there. One say 25, one say 12.
12 billion.
So must be between there.
Somewhere in between.
So around 20. So according to you, how many billions of years?
Big Bang, the dating of the Big Bang, yeah.
13 billion years.
13.
13 billion years.
13.
13 billion.
Oh, that's, I think, good. 13.
Well, that was a very nice session, and thank you, Your Holiness, and thank the speakers, Professor Mou, and I guess myself. And also thank the audience. Please, if you're interested, we will have another open discussion this afternoon.